We are creatures of the momentary sleaze. Our lives are governed by the rising of a sun and the rhythmic beating of a heart cycle so brief they barely register against the backdrop of the world around us. Yet, we possess a peculiar obsession with the concept of forever. We look at the stars and assume they have always been there, steady and unchanging, acting as silent witnesses to our fleeting history. But as we look deeper into the void, we begin to realize that the cosmos is not a static stage. It is a process, a slow-burning event that had a specific beginning and is hurtling toward an inevitable conclusion. The difficulty lies in our perception. Our minds are not built to calculate billions of years, just as our eyes are not built to see the curvature of the dark. We find ourselves standing in a narrow window of time, trying to decipher the age of a structure so vast that its earliest moments are almost beyond our reach. To understand when the universe will end, we must first confront the terrifying scale of its existence and the subtle clues it has left behind in the light. This journey requires us to look past the familiar ticking of our clocks and into the deep, silent rhythms of space itself, where time behaves in ways that defy our intuition. The question arrives like a whisper in the dark. When did all of this begin? For millennia, the question seemed not only unanswerable, but unnecessary. The universe, as our ancestors understood it, simply was. Stars wheeled overhead in their predictable courses. Seasons turned. Rivers flowed. There was no need to imagine a moment of inception because the cosmos appeared eternal. A stage upon which human drama unfolded, but which itself remained unchanging, infinite in both directions. To ask when the universe began was to ask when a circle starts. The question itself seemed malformed. A category error born of applying finite thinking to the infinite. But something shifted in our understanding. Slowly, across centuries of observation and mathematics, a different picture emerged. The universe was not static. It was not a passive container. Evidence accumulated that everything around us, every galaxy, every atom, every quantum of light exists within a dynamic structure that evolves, expands, and bears the signature of a definite origin. This realization did not arrive all at once. It came through careful measurement, through the patient work of mapping distances to distant galaxies, through the discovery that light itself carries information about the motion of its source. When astronomers noticed that galaxies were receding from us, their light stretched toward the red end of the spectrum, they glimpsed something profound. The universe is growing larger. If space itself is expanding, then running the process backward in time leads inevitably to a moment of compression. A state where all distances collapsed toward zero. Where the separation between here and there vanished into a singularity of unimaginable density and heat. This was not merely an explosion in space, but an explosion of space itself, an event so fundamental that asking what came before it may be as meaningless as asking what lies north of the North Pole. Time, as we experience it, may have emerged from that moment alongside space and matter and energy. The question of the universe's age thus becomes the question of time's own beginning. Yet measuring this age presents a paradox. We are embedded within the very system we seek to measure. Every clock we build, every observation we make, every calculation we perform occurs inside the timeline itself. We cannot step outside to view the cosmos from some neutral vantage point. We are like characters in a novel, attempting to determine when the first page was written, using only clues found within the text itself. Our measurements are conducted from a particular location, a small planet orbiting an ordinary star in an unremarkable galaxy, and they are necessarily shaped by the local properties of spacetime in our vicinity. Time does not flow uniformly throughout the cosmos. It bends around massive objects. It dilates with velocity. The very ruler we use to measure cosmic duration is itself flexible, stretched and compressed by the geometry of the universe. This is where the evidence becomes both elegant and strange. Across the entire sky, in every direction we look, there exists a faint glow of microwave radiation. This cosmic microwave background is not the light from stars or galaxies, but something far more ancient, a relic from a time when the universe was so hot and dense that matter and light existed in a plasma state, a primordial soup where photons scattered endlessly off free electrons. As the universe expanded and cooled, there came a moment when atoms could finally form, when electrons bound themselves to nuclei, and light could at last travel freely through space. The photons released at that moment have been journeying through the cosmos ever since, stretched by the expansion of space from visible light into the microwave spectrum. This radiation is the oldest light we can observe, a snapshot of the universe when it was roughly 380,000 years old. The cosmic microwave background offers a window into deep time, but it is a window that requires careful interpretation. The temperature of this radiation is remarkably uniform, varying by only tiny fractions of a degree across the sky. These minute fluctuations encode information about the density variations in the early universe, the seeds from which galaxies and galaxy clusters would eventually grow. By analyzing the pattern of these fluctuations, scientists can infer the conditions that prevailed in the primordial cosmos: the density of matter, the distribution of energy, the geometry of space itself. It is a kind of archaeology conducted not with shovels and brushes, but with telescopes and equations. Reading the history of the universe written in the structure of its oldest observable light. Yet the act of reading this history immediately confronts us with the problem of time's relativity. The photons we detect today have traveled for billions of years to reach us, crossing a universe that has been expanding all the while. The distance they have covered is not simply their speed multiplied by the time elapsed, because space itself has been stretching during their journey. A galaxy that emitted light 1 billion years after the beginning of the universe is not now 1 billion light-years away. The expansion of space has carried it much farther. The relationship between distance and time becomes a complex function of the universe's expansion rate, which itself has changed over cosmic history. Measuring the age of the universe thus requires modeling this expansion, understanding how the rate has evolved, and working backward to the moment when all distances were zero. This expansion is not uniform in its effects on time. General relativity teaches us that massive objects warp the fabric of spacetime, causing time to pass at different rates depending on proximity to matter and energy. Near a black hole, time slows dramatically relative to distant observers. On Earth, time runs slightly faster at high altitude than at sea level, an effect confirmed by atomic clocks. Across cosmological scales, the distribution of matter and the overall geometry of space influence the passage of time in ways that complicate any simple notion of a universal clock. When we speak of the universe's age, we are implicitly referring to a particular frame of reference, cosmic time coordinate, defined by observers who move with the general expansion, who see the cosmic microwave background as nearly isotropic, the same in all directions. Our attempt to measure cosmic time thus rests on a choice of perspective. We adopt the viewpoint of a comoving observer, one who rides along with the expansion, whose local patch of space stretches uniformly in all directions. From this frame, we can define a cosmic time, a shared temporal coordinate that allows us to speak meaningfully of now across vast distances. This is the time that appears in cosmological models, the parameter that tracks the evolution of the universe from its hot, dense beginning to its current cool, dilute state. But this cosmic time is an abstraction, a mathematical construct built from observational data and theoretical assumptions. It is not something we can directly measure with a stopwatch. It must be inferred. The inference proceeds through multiple lines of evidence, each offering an independent constraint on the universe's age. The cosmic microwave background provides one crucial data set: its temperature, its spectrum, and the precise pattern of its fluctuations all depend on cosmological parameters, including the total age, the density of ordinary matter, the abundance of dark matter, and the influence of dark energy. By fitting theoretical models to these observations, researchers can extract estimates of these parameters with remarkable precision. The age derived from this analysis depends on getting the model right, on correctly accounting for all the physical processes that shaped the early universe. A second line of evidence comes from the observation of distant galaxies and the measurement of cosmic expansion. By determining how quickly galaxies at various distances are receding from us, we can infer the current expansion rate, a quantity known as the Hubble constant. If we know this rate and understand how it has changed over time, we can calculate how long the expansion has been underway. This method requires careful calibration. Measuring distances to faraway galaxies is not straightforward. Astronomers rely on a cosmic distance ladder, a series of overlapping measurement techniques that extend from nearby stars to the most remote objects in the observable universe. Each rung of this ladder introduces uncertainty, and discrepancies between different methods have led to ongoing debates about the precise value of the Hubble constant. Yet another approach involves the ages of the oldest stars. Stars evolve in predictable ways, burning through their nuclear fuel at rates determined by their mass and composition. By studying ancient stars in globular clusters, dense, spherical collections of stars that orbit our galaxy, astronomers can estimate when these objects formed. The universe cannot be younger than its oldest stars, so these stellar ages provide a lower bound on cosmic time. The measurements align well with estimates from other methods, lending confidence to the overall picture. Though they too carry uncertainties related to stellar physics and the interpretation of observational data. What emerges from these converging lines of evidence is a consistent, if complex, portrait of cosmic history. The universe is approximately 13.8 billion years old, give or take a few tens of millions of years. This number represents the time elapsed, according to our moving cosmic clock, since the moment when space and time emerged from the initial singularity. But even this figure carries subtle layers of meaning. It is the age measured in the rest frame of the cosmic microwave background, the frame in which that ancient radiation appears uniform. An observer moving at high velocity relative to this frame would measure a different elapsed time, though such observers are not the ones defining cosmological time in our models. The precision of this age estimate masks the profound conceptual difficulty underlying it. We are measuring duration using a framework, general relativity, that treats time as a dimension intertwined with space, subject to distortion and curvature. The age of the universe is not an absolute quantity etched into the fabric of reality, but a coordinate-dependent measure, meaningful within a particular choice of reference, frame, and cosmic model. Different solutions to Einstein's equations, different assumptions about the universe's composition and geometry yield different age estimates. The fact that multiple independent observations converge on a similar number gives us confidence. But it does not erase the fundamental limitation. We are creatures within spacetime, attempting to measure spacetime's own extent. This limitation becomes even more apparent when we consider the edges of our observational reach. Light travels at a finite speed, and the universe has existed for a finite time, which means there is a boundary to what we can see, a cosmic horizon, beyond which light has not had time to reach us. This horizon is not a physical barrier, but an observational limit, a consequence of the intersection between the age of the universe and the speed of light. Objects beyond this horizon exist in principle, but they are forever inaccessible to our telescopes. We cannot measure their distances, determine their properties, or include them in our accounting of cosmic history. The universe we observe is a subset of the total universe, a sphere centered on our location whose radius is defined by how far light could have traveled since the beginning. Moreover, the expansion of space introduces a further wrinkle. As light travels toward us from distant sources, the space through which it moves is itself stretching. This means that the most distant objects we can observe are now much farther away than the distance their light has traveled. The observable universe is larger than its age, multiplied by the speed of light. This stretching of space also affects the relationship between redshift, the degree to which light is shifted toward longer wavelengths and distance. Redshift becomes a proxy for cosmic time, a way of labeling epochs in the universe's history. But translating redshift into an actual elapsed time requires detailed modeling of the expansion history. These complexities reveal the true challenge of measuring eternity from within. We construct models, we gather data, we refine our estimates, but every conclusion is contingent on assumptions about physics, about the uniformity of the universe on large scales, about the constancy of natural laws across space and time. We assume that the speed of light has not changed, that the fundamental constants governing nuclear reactions in stars were the same billions of years ago as they are today. That general relativity correctly describes gravity on cosmological scales. These assumptions are well tested within our local cosmic neighborhood. But extending them across billions of light-years and billions of years in time is an act of inference, not direct measurement. The age of the universe, then, is both a triumph of human ingenuity and a reminder of our limits. It represents the culmination of centuries of observation, theory, and calculation, a number wrung from the faint whispers of ancient light, from the motions of galaxies, from the life cycles of stars. Yet it is also a measure that exists only within a framework we have constructed, a coordinate in a model designed to make sense of observations made from our particular vantage point. Time is not a river flowing uniformly past all observers. It is woven into the structure of the cosmos, flexible and relative, shaped by matter and energy, by motion and gravity. To measure the universe's age is to navigate this intricate geometry, to find our place within a vast, expanding tapestry whose beginning we can glimpse but never fully grasp from the inside. The measurement stands precise and powerful, yet always tinged with the awareness that we are reading the clock embedded in the very fabric we seek to understand. The human mind is a timepiece calibrated to the immediate. It tracks the rhythm of breath, the beat of the heart, the cycle of waking and sleeping. These are the temporal scales that matter for survivals: seconds, minutes, hours, the passage of days and seasons. Our neural architecture evolved to navigate a world where decisions unfold across moments, where danger arrives in heartbeats, where the relevant future extends perhaps to the next harvest or the coming winter. We are exquisitely sensitive to change within this narrow window, attuned to the subtle shifts in light that mark dawn and dusk, to the gradual lengthening of shadows as the sun arcs overhead. But this precision comes at a cost. The same cognitive apparatus that allows us to perceive the flight of an arrow or the ripening of fruit struggles when confronted with durations that dwarf human experience. Consider the sensation of a year. For a child, a year feels immense, stretching into what seems like eternity as they wait for a birthday or holiday. For an adult, years begin to compress, each one a smaller fraction of accumulated experience. Yet even a centurious span that exceeds most human lifetimes, something we can almost grasp through stories. Through the lives of grandparents and the memory of historical events within living memory, we can imagine, with effort, the passage of 1,000 years by thinking of medieval castles or ancient empires. 10,000 years brings us to the threshold of recorded history, to the dawn of agriculture and the first cities. Our mental tools begin to strain here, but we can still anchor ourselves with artifacts, with ruins, with the continuity of human culture. Beyond this point, the scaffolding collapses. 1,000,000 years ceases to be a duration we can feel or visualize. It becomes an abstraction, a number on a page. The human brain has no mechanism for experiencing such intervals directly. We cannot hold 1,000,000 years in working memory the way we hold the image of yesterday's sunset or the anticipation of tomorrow's meal. The number exists, we can perform calculations with it, but it does not translate into intuition. And this is only the beginning of the problem, because the universe operates on scales that make 1,000,000 years seem trivial. The Earth itself is approximately 4.5 billion years old. To put this in perspective, if we compressed the entire history of our planet into a single year, modern humans would appear only in the final minutes before midnight on December 31st. Dinosaurs would have emerged in mid-December and vanished on the 26th. The first multicellular life would not appear until late November. For the majority of this imaginary year, Earth would be a world of single cells, an ocean punctuated by bare rock, slowly evolving in ways invisible to any hypothetical observer. And yet, this immense span, longer than our minds can properly conceive, is itself less than a third of the age of the universe. Our biological clocks offer no preparation for such magnitudes. The circadian rhythm that governs sleep and wakefulness is synchronized to the rotation of the Earth. A 24-hour cycle refined over hundreds of millions of years of evolution. Seasonal migrations, reproductive cycles, the flowering of plants all are tied to the orbit of our planet around the Sun, a yearly dance that defines the tempo of terrestrial life. Even the slower rhythms we recognize, the gradual erosion of mountains or the drift of continents, unfold on timescales of millions to tens of millions of years. These geological processes creep at a pace imperceptible within a human lifetime. Yet they are rapid compared to the evolution of stars or the expansion of the universe. Stars age across billions of years. A star like our Sun will burn steadily for roughly 10 billion years, fusing hydrogen into helium in its core, maintaining a delicate balance between gravitational collapse and the outward pressure of nuclear fusion. From a human perspective, the Sun appears eternal, unchanging except for the daily cycle of rising and setting. Ancient astronomers saw the same Sun we see today, and in all likelihood, humans thousands of generations from now will witness it in much the same state. The changes occurring within the Sun, the gradual accumulation of helium ash, the slow increase in luminosity are invisible on timescales, meaningful to biological life. A million years of stellar evolution might alter the Sun's output by a fraction of a percent. A shift is subtle, to detect without precise instruments and the patience to compare measurements across epochs. This mismatch between biological perception and cosmic reality creates a profound barrier to understanding. When we speak of the universe being 13.8 billion years old, we are invoking a number that has no experiential correlate. It is not that the number is inaccurate or that the measurements are flawed. The evidence is robust, converging from multiple independent sources. But the duration itself exists outside the domain of human intuition. We can say billions of years as easily as we say 3 seconds, yet the two phrases invoke entirely different cognitive processes. 3 seconds is something we can count, feel, live through. Billions of years is a concept we accept intellectually while remaining emotionally disconnected from its true enormity. Language itself betrays this limitation. We use metaphors to bridge the gap, the age of the Earth compared to a calendar year, the history of the universe compressed into a single day, but these analogies ultimately fail. They reduce cosmic time to human time, forcing an incomprehensibly vast duration into a familiar frame. The compression is so extreme that it distorts rather than clarifies. If the universe's entire history were a 24-hour day, the emergence of humans would occupy less than the final second. Life on Earth would span only a few hours. The formation of our solar system would occur in the late afternoon. The metaphor makes the timeline comprehensible, but at the cost of flattening the texture of deep time, of obscuring the immense spans during which almost nothing, from a human perspective, seemed to happen. This cognitive barrier has consequences for how we understand our place in the cosmos. The immediacy of human concerns, politics, personal relationships. The anxieties of daily life occupies the full bandwidth of conscious attention. The universe's vast age recedes into abstraction, a piece of trivia rather than a felt reality. We know intellectually that the atoms in our bodies were forged in the cores of dying stars billions of years ago, that the light reaching our eyes from distant galaxies began its journey long before Earth existed. But this knowledge rarely penetrates the intuitive layers of thought. It remains external, a fact learned rather than a truth integrated into our perception of time. The difficulty is not merely one of scale, but of relevance. Evolution shaped our cognitive apparatus to prioritize information useful for survival and reproduction within a social context. The position of the sun matters because it tells us when to hunt or gather. The phases of the moon matter because they correlate with tides and animal behavior. The memory of where food was found last season matters because it increases the likelihood of finding food again. But the age of the universe, the life cycle of a star, the expansion of space, these operate on scales so removed from biological imperatives that our brains have no native circuitry for processing them. They are not threats, not opportunities, not socially significant. They are simply backdrop, and evolution does not waste neural resources on irrelevant backdrop. Yet this backdrop is the stage upon which everything unfolds. The stars that appear fixed and eternal are in fact temporary structures born from collapsing clouds of gas living out their nuclear lives and eventually dying in explosions or gentle exhalations that seed space with the raw materials for new generations of stars and planets. Galaxies, those vast islands of stars visible as faint smudges through telescopes, are dynamic systems that collide and merge over hundreds of millions of years, reshaping themselves through gravitational interactions that play out in what we might call slow motion. Were we capable of perceiving motion on such scales? The cosmic microwave background, that faint glow of ancient light we detect in every direction, has been cooling and redshifting for more than 13 billion years. A process so gradual that its temperature has dropped by less than 1,000th of a degree over the entire span of human existence. Our perception of now is itself an illusion constructed by the brain. Neuroscience reveals that conscious awareness lags behind sensory input by tens to hundreds of milliseconds, a delay during which the brain processes and integrates information before presenting it to conscious experience as a unified present moment. This constructed now typically encompasses a window of a few seconds, the duration across which events feel simultaneous or closely connected. Anything outside this window becomes past or future, accessible through memory or anticipation, but not directly experienced. The cosmic now, the set of events occurring simultaneously across the universe in some reference frame, say, a radically different concept, one that requires sophisticated physics to even define properly, and which bears no relationship to the felt sense of present moment awareness. This disconnect extends to our perception of change. Humans are remarkably adept at detecting motion, at noticing when something in the visual field shifts position. This ability is crucial for tracking prey, avoiding predators, and navigating complex environments. But the kinds of change that matter cosmologically, the gradual brightening of a star as it exhausts its fuel, the slow drift of a galaxy across the sky due to its proper motion through space, the imperceptible expansion of the universe itself, these occur at rates far below the threshold of human perception. Even time-lapse photography, which compresses hours into seconds to show flowers opening or clouds racing across the sky, cannot make cosmic evolution visible. No amount of speed-up can render the life cycle of a star into something a human could watch unfold, because the required compression factor is beyond what any medium can represent while maintaining meaningful detail. The invention of abstract notation mathematics, written records, timelines allowed humanity to transcend some of these limitations. We can represent 1 billion years as easily as we represent a single year by simply writing the number. We can construct graphs where the horizontal axis spans eons, placing events in proper sequence even if we cannot feel the intervals between them. This abstraction is powerful. It permits science, enables us to discover and communicate truths about timescales utterly alien to direct experience. But abstraction is not understanding in the visceral sense. A child who learns that the universe is nearly 14 billion years old has acquired a fact, but has not gained an intuitive grasp of what that duration means, any more than memorizing the distance to a star in light years, conveys the experiential reality of such a void. Religious and philosophical traditions have long grappled with eternity, with the infinite, with durations beyond mortal comprehension. These concepts often serve as pointers toward the transcendent, toward aspects of existence that exceed human categories. The cosmological deep time revealed by modern science occupies a similar conceptual space, not infinite, but so vast as to function as infinity for all practical cognitive purposes. The difference is that cosmic time is measurable, bounded, and subject to empirical investigation. It is not a mystical abstraction, but a feature of physical reality that can be studied, refined, and better understood, even if it can never be fully internalized by minds built for entirely different temporal scales. There is a peculiar loneliness to this realization. We are beings of the moment, trapped in the narrow window of the present, watching a universe that evolves in majestic slow motion across spans of time that render our entire species a fleeting anomaly. The stars we see tonight are not the stars as they are now, but as they were when their light began its journey, toward us in some cases, thousands or millions of years ago. We are always looking into the past when we look outward into space, and the deeper we look, the further back we see. The most distant galaxies visible to our telescopes appear as they were when the universe was young, not as they exist in any present moment we could meaningfully share with them. This temporal displacement is built into the structure of observation itself. Light travels fast by human standards, fast enough to circle the Earth more than 7 times in a single second, but cosmological distances are so immense that even light requires eons to cross them. There is no way to see the universe as it is now across its full extent, because now is a local concept that breaks down when applied to regions separated by billions of light years. What we observe is a patchwork of different cosmic epochs, all arriving at our detectors simultaneously, but originating from vastly different times in the universe's history. Our biological clocks, then, are not merely inadequate for cosmic time, they are fundamentally incompatible with it. We live in a universe that operates according to rhythms we cannot feel, that changes in ways we cannot directly perceive, that extends across durations we cannot intuitively comprehend. This is not a deficiency of the human mind, but a consequence of its design. Evolution optimized us for survival in a particular niche, at a particular scale, and that optimization necessarily excluded the cosmic. We are local creatures attempting to understand a non-local reality, temporal beings trying to grasp deep time, finite minds confronting durations that mock our sense of permanence. Yet within this mismatch lies something remarkable. Despite our limitations, we have developed tools, mathematical, observational, theoretical, that allow us to map the unmappable, to measure the immeasurable. We cannot feel a billion years, but we can calculate it, model it, test our models against evidence. We cannot watch a star evolve, but we can observe thousands of stars at different stages of their lives and piece together the narrative. Our minds may be clocks set to the rhythm of days and seasons, but our science extends far beyond the reach of our senses into realms of time, where human intuition falls silent and only careful reasoning can guide us. The cosmic void remains vast, indifferent to our temporal limitations, but we have learned to read its history in the light that reaches us across the abyss, decoding messages written in wavelengths and redshifts in the faint echoes of events that transpired long before our world existed. Light carries memory. Every photon that reaches our instruments has traveled through space for some duration, crossing distances that encode information not only about the source that emitted it, but about the journey itself. When astronomers collect light from distant galaxies, they are not merely observing objects separated from us by vast reaches of emptiness. They are witnessing events that occurred in the deep past, moments frozen in electromagnetic radiation that has been traveling toward us across eons. This is not metaphor. It is the literal consequence of light's finite speed combined with the immense scales of the cosmos. The speed of light in vacuum is constant, roughly 300,000 kilometers per second. Nothing with mass can reach this speed, and nothing can exceed it. This cosmic speed limit, predicted by Einstein's special relativity and confirmed through countless experiments, means that information cannot propagate instantaneously across space. When we observe a star 10 light-years away, we see it as it was 10 years ago. The light now entering our telescopes left that star a decade in the past. For more distant objects, the time delay becomes correspondingly greater. A galaxy 1 million light-years away appears as it existed 1 million years ago. The most remote galaxies detectable by our instruments emit light that has been traveling for billions of years, crossing a universe that has changed profoundly during the photon's journey. But the universe is not merely a static arena through which light propagates. Space itself is dynamic, expanding, carrying galaxies away from one another in a process that has no center and no edge. This expansion was first inferred from observations made in the early 20th century, when astronomers noticed a peculiar pattern in the light from distant galaxies. The spectral lines, distinct wavelengths where atoms absorb or emit light, were systematically shifted toward the red end of the spectrum. The farther away a galaxy, the greater the redshift. This was not the result of galaxies moving through space in the conventional sense, but rather a consequence of space itself stretching during the time light was in transit. Imagine a photon emitted from a distant galaxy billions of years ago. At the moment of emission, the photon has a specific wavelength determined by the physics of the atom that released it. As the photon travels through space, the fabric of that space is expanding, and the expansion gently stretches the wavelength of the photon along with it. By the time the photon reaches our detectors, its wavelength has increased. What was emitted as ultraviolet light might arrive as visible light. What began as visible light might arrive as infrared. The degree of stretching depends on how much the universe has expanded during the photon's journey, which in turn depends on the distance traveled and the history of the expansion rate. This redshift is quantified by comparing the observed wavelength to the wavelength the light had when emitted. A redshift of 1 means that wavelengths have doubled. A redshift of 2 means they have tripled. The most distant galaxies observed have redshifts exceeding 10, indicating that the universe has expanded by more than a factor of 11 since the light we now detect left those galaxies. Redshift thus becomes a proxy for both distance and time, a way of labeling epochs in cosmic history. High redshift corresponds to the distant past, to a universe that was smaller, denser, and hotter than it is today. The relationship between redshift and time is not linear. It depends on the detailed history of how fast space has been expanding at each moment since the beginning. This expansion rate is governed by the contents of the universe of matter, radiation, and energy that curve spacetime according to Einstein's general relativity. In the early universe, when everything was compressed into a smaller volume, the density of matter and radiation was much higher, and gravity was attempting to slow the expansion. As space grew and density dropped, the influence of matter weakened. More recently, observations suggest that a mysterious component called dark energy has come to dominate, accelerating the expansion rather than slowing it. To understand redshift rigorously requires understanding the metric of spacetime, the mathematical description of how distances and durations are measured in an expanding universe. In a static universe, distances would be straightforward. Light would travel in straight lines at constant speed, and the distance to an object would simply be the speed of light multiplied by the travel time. But in an expanding universe, the situation is more subtle. The distance between 2 points grows over time, not because the points are moving through space, but because new space is being created between them. A photon traveling from a distant galaxy to us is not moving through a fixed distance, but rather traversing a distance that is itself increasing during the journey. This creates a conceptual puzzle. If space is expanding, how do we even define distance? Do we mean the distance at the time the light was emitted, the distance at the time it is received, or some average over the journey? Cosmologists adopt a particular convention, defining what is called the comoving distance, a distance coordinate that expands with the universe and treats the walk expansion as a scaling of space itself rather than a motion through space. In this framework, galaxies that participate in the cosmic expansion remain at fixed comoving coordinates, while the physical separation between them grows as the scale factor of the universe increases. The scale factor is a dimensionless number that describes how much the universe has grown relative to some reference time. If we set the scale factor to 1 at the present moment, then at earlier times it was smaller. At the moment of the Big Bang, the scale factor was 0, corresponding to infinite density and temperature singularity where the equations of general relativity break down. As time progressed, the scale factor increased, space expanded, and the density and temperature dropped. The relationship between redshift and scale factor is direct. A redshift of z corresponds to a scale factor of 1 divided by 1 plus z. A redshift of 1 means the universe was half its current size when the light was emitted. A redshift of 9 means it was 1/10 its current size. This expanding space is not expanding into anything. There is no external arena within which the universe grows. Space itself is all there is, and its expansion is an intrinsic property described by the geometry of spacetime. The expansion does not have a center. Every point in space sees every other distant point receding, and from any vantage point, the universe appears to expand uniformly in all directions. An observer in a galaxy billions of light-years from us would measure the same cosmic expansion rate, see the same redshifts in their observations of distant galaxies, and conclude, just as we do, that they reside in an expanding universe. The uniformity of this expansion is captured by what is known as the cosmological principle, the assumption that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that it looks the same at every location. Isotropic means it looks the same in every direction. Observations of the cosmic microwave background and the large-scale distribution of galaxies support this principle. While there are local variations, clusters of galaxies, voids, the lumpy structure we observe when averaged over scales of hundreds of millions of light-years. The universe appears remarkably uniform. This uniformity simplifies the task of modeling cosmic evolution. If the universe is homogeneous and isotropic, its dynamics can be described by a single function, the scale factor as a function of time. The equations governing this scale factor are the Friedmann equations derived from Einstein's general relativity under the assumption of a uniform universe. These equations relate the expansion rate to the density of matter, radiation, and dark energy, allowing us to connect observations of redshift and distance to theoretical predictions about cosmic history. The Friedmann equations reveal that the universe's fate and past are determined by its contents. A universe dominated by matter expands, but decelerates over time, with gravity working to pull everything back together. A universe dominated by radiation expands even faster in the early stages, when radiation density is highest. A universe with a cosmological constant A form of dark energy that remains at constant density even as space expands can accelerate in its expansion, with the repulsive effect of dark energy overpowering the attractive pull of matter. Current observations indicate that our universe has transitioned through these regimes. In the earliest moments, radiation dominated. As the universe expanded and cooled, matter took over. More recently, dark energy has become the dominant component, driving an accelerated expansion that will continue indefinitely if present trends persist. The concept of dark energy emerged from observations of distant supernova, exploding stars that serve as cosmic distance markers. By measuring the brightness and redshift of these supernova, astronomers can determine how the expansion rate has changed over time. The surprising discovery, announced in the late 1990s, was that distant supernova appeared dimmer than expected, implying that they were farther away than a simple extrapolation of the expansion rate would predict. This could only be explained if the expansion of the universe had been accelerating. Some form of energy with negative pressure-repulsive gravity was required to account for the observations. Whether this dark energy is truly a cosmological constant, a property of empty space itself, or something more exotic, remains one of the deepest mysteries in cosmology. The stretching of light by expansion has another profound implication. It allows us to probe the thermal history of the universe. In the early moments after the Big Bang, the universe was extraordinarily hot and dense. Particles collided with such ferocity that atoms could not form. Protons and electrons existed in a plasma, and photons scattered constantly off the free electrons, unable to travel far before interacting. As the universe expanded, it cooled. Eventually, roughly 380,000 years after the beginning, the temperature dropped low enough for electrons to bind to nuclei, forming the first neutral atoms. With free electrons swept up into atoms, photons could suddenly travel unimpeded. The universe became transparent, and the light from this epoch has been traveling freely ever since. We observe this ancient light today as the cosmic microwave background. When it was emitted, the temperature of the universe was around 3,000 degrees, hot enough to glow in the visible spectrum. But the expansion of space has stretched those photons over the intervening billions of years, redshifting them from visible light into the microwave portion of the spectrum. The temperature of this radiation has dropped to just under 3 degrees above absolute zero, a direct measure of how much the universe has expanded since the light was released. The cosmic microwave background has a redshift of approximately 1090, meaning the universe is about 1090 times larger now than it was when this light began its journey. This background radiation is astonishingly uniform, varying in temperature by only 1 part in 100,000 across different directions in the sky. These tiny fluctuations are critical. They represent the seeds of all structure in the universe's light density variations in the primordial plasma that, under the influence of gravity, would eventually grow into galaxies, stars, and planets. By mapping the pattern of these fluctuations, cosmologists can infer the properties of the early universe with remarkable precision. The density of ordinary matter, the abundance of dark matter, the geometry of space, and the parameters that govern cosmic expansion. The geometry of space itself is tied to the expansion. General relativity permits 3 possible geometries for a homogeneous isotropic universe: flat, positively curved, or negatively curved. A flat universe is analogous to Euclidean space, where parallel lines remain parallel forever. A positively curved universe is like the surface of a sphere, where parallel lines eventually converge. A negatively curved universe resembles a saddle, where parallel lines diverge. The geometry depends on the total energy density of the universe relative to a critical value. Observations of the cosmic microwave background indicate that our universe is very close to flat, with a total energy density almost exactly equal to the critical density. This flatness is not a trivial result, requires a precise balance between the kinetic energy of expansion and the induced potential energy of matter and dark energy. The flatness of the universe has implications for its ultimate fate. A flat or negatively curved universe will expand forever, gradually cooling and diluting as matter spreads across ever greater volumes. A positively curved universe with sufficient matter density could eventually halt its expansion and recollapse into a big crunch. Given the observed acceleration driven by dark energy, eternal expansion seems far more likely. The universe will not end in a cataclysmic collapse, but in a gradual fade, stars exhausting their fuel, galaxies drifting apart beyond the reach of light, and eventually, in the unimaginably distant future, even black holes evaporating through quantum processes, leaving behind a cold, diffuse sea of radiation. The mechanics of expansion also clarify why distant galaxies are not violating the cosmic speed limit. While no object can move through space faster than light, space itself has no such restriction. Two galaxies can recede from each other faster than light if there is sufficient expanding space between them. This does not involve any object moving superluminally through its local spacetime. Each galaxy remains nearly at rest in its own comoving reference frame. It is the accumulation of expanding space over vast distances that produces recession velocities exceeding the speed of light. Light emitted from such galaxies can still eventually reach us, though it may take longer than the naive calculation of distance divided by the speed of light would suggest, because the light itself must traverse expanding space. This interplay between light, expansion, and geometry defines the observable universe. There is a horizon beyond which light has not had sufficient time since the Big Bang to reach us, even accounting for the expansion of space. This cosmological horizon is not static. It grows as the universe ages, allowing light from ever more distant regions to arrive. Yet the accelerating expansion means that galaxies currently beyond a certain distance will never become observable, no matter how long we wait. The space between us and them is expanding faster than light can traverse it. They are receding beyond the edge of what is, in principle, accessible to observation. Understanding the first light, the cosmic microwave background, that mechanism of expansion provides the foundation for calculating the age of the universe. By measuring the current expansion rate, determining the proportions of matter, and dark energy, and tracing back through the history encoded in redshifts and the microwave background, cosmologists construct a timeline. The universe began in a hot, dense state nearly 14 billion years ago. Space has been expanding ever since, cooling and diluting, allowing structures to form and complexity to emerge. The photons we detect today from the cosmic microwave background and distant galaxies are messengers from that history. Their wavelengths stretched by the journey, carrying information about epochs long past. In studying these photons, we are not merely looking outward into space, but backward into time, assembling a chronicle of the cosmos written in light itself. Distance is the silent problem that haunts every attempt to map the universe. When we look at a star or galaxy in the night sky, we see light, we measure brightness, we record spectra. But how far away is it? Without knowing the distance, we cannot determine the object's true luminosity, its size, or its relationship to other structures in space. A dim object nearby and a brilliant object far away can appear identical to our instruments. Disentangling these possibilities requires a method for measuring cosmic distances independently of brightness alone. And for much of human history, no such method existed beyond the nearest stars. The breakthrough came through the discovery of objects whose intrinsic properties could be inferred from their behavior, objects that shine with a predictable luminosity, allowing astronomers to use them as standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, the difference tells you the distance. The light from any source diminishes with the square of the distance traveled. An object twice as far away appears 4 times dimmer. An object 10 times more distant appears 100 times fainter. This inverse square law is fundamental to the geometry of light spreading through space, and it transforms the problem of measuring distance into the problem of identifying objects with known luminosity. Among the first reliable standard candles were Kephide variable stars. These are giant stars that pulsate regularly, swelling and contracting over periods ranging from days to months. The pulsations are not random. They arise from a knot stability in the star's outer layers, self-regulating cycle where increased opacity during contraction heats the star, causing it to expand and cool, which then triggers another contraction. What makes Kephide invaluable is a relationship discovered in the early 20th century. The period of pulsation is directly related to the star's intrinsic luminosity. A Kephide that pulsates slowly is intrinsically brighter than one that pulsates rapidly. By measuring the period, astronomers can deduce the true luminosity, and from that, calculate the distance. This period luminosity relationship transformed astronomy. It allowed Edwin Hubble, working at Mount Wilson Observatory in the 1920s, to identify kipsides in what were then called spiral nebulae fuzzy patches of light, whose nature was disputed. By measuring the periods of these kipsides and calculating their distances, Hubble demonstrated that these nebulae were far beyond the boundaries of our own galaxy. They were galaxies in their own right, island universes millions of light-years away. This revelation expanded the known cosmos by orders of magnitude and laid the groundwork for understanding cosmic expansion. Hubble went on to measure the redshifts of these galaxies and discovered that the farther away they were, the faster they appeared to be receding. The universe was not static. It was growing. But Cephids have limitations. They are bright enough to be detected in nearby galaxies. But beyond a certain distance, roughly 100 million light-years, they become too faint to observe individually, even with powerful telescopes. To probe deeper into space and further back in time, astronomers needed a brighter standard candle. They found it in a particular type of stellar explosion, the type Ia supernova. A type Ia supernova occurs in a binary star system, where a white dwarf, the dense remnant of a sun-like star, accretes material from a companion. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. But this support has a limit, known as the Chandrasekhar limit. Approximately 1.4 times the mass of the Sun. If a white dwarf accumulates enough material to reach this threshold, it can no longer support itself. The core ignites in a runaway thermonuclear explosion, disintegrating the star in a matter of seconds and releasing as much energy as the Sun will emit over its entire 10 billion-year lifetime. What makes type Ia supernova useful as standard candles is their remarkable consistency, because they all result from white dwarfs reaching essentially the same critical mass. The explosions have similar peak luminosities. At maximum brightness, a type Ia supernova can outshine an entire galaxy, making it visible across billions of light-years. By measuring the apparent brightness of such an event and comparing it to the known intrinsic luminosity, astronomers can calculate the distance to the host galaxy with considerable precision. This technique extended the cosmic distance ladder far beyond the reach of Cepheid variables, into the realm where the expansion history of the universe becomes directly measurable. The process is meticulous. Telescopes scan large patches of sky repeatedly, searching for the sudden appearance of a new bright point of light. When a candidate supernova is detected, follow-up observations determine its spectrum and light curve, the way its brightness changes over time. Type Ia supernova have characteristic spectral signatures and a distinctive rise and fall in brightness. Once confirmed, the supernova's peak brightness is measured carefully, corrected for any dimming by dust along the line of sight, and compared to the expected intrinsic luminosity. The redshift of the host galaxy provides the recession velocity, and together, distance and redshift map out the expansion rate of the universe at different epochs. In the 1990s, two independent teams used type Ia supernova to probe the expansion history with unprecedented detail. They observed dozens of distant supernovae, expecting to find that the expansion of the universe was decelerating under the pull of gravity. Instead, they found something startling. The distant supernovae were dimmer than expected, implying they were farther away than a decelerating universe would place them. The only explanation consistent with the data was that the expansion had been accelerating. Some form of dark energy exerting a repulsive gravitational effect was driving the universe to expand faster and faster. This discovery, honored with the Nobel Prize in Physics, fundamentally altered our understanding of the cosmos and revealed that roughly 70% of the universe's total energy density exists in this mysterious dark energy component. The reliability of type Ia supernova as standard candles depends on understanding their physics in detail. While they are remarkably uniform, they are not perfectly identical. Variations in the exact conditions of the explosion, differences in the composition of the white dwarf, the rate of accretion, the spin of the star can produce supernovae that are slightly brighter or dimmer than average. Astronomers have developed techniques to account for these variations. One key observation is that brighter type Ia supernovae tend to fade more slowly than dimmer ones. By measuring the shape of the light curve, observers can standardize the peak luminosity, correcting for intrinsic differences and improving the precision of distance measurements. Even with these corrections, uncertainties remain. Dust in the host galaxy or in our own Milky Way can absorb and scatter light, making supernova appear dimmer and thus seemingly more distant. Disentangling the effects of dust from genuine cosmological dimming requires careful analysis of colors and spectra. Systematic errors in these corrections can propagate through the entire distance ladder, affecting estimates of the expansion rate and, ultimately, the calculated age of the universe. This is why multiple independent methods are essential, cross-checking distances derived from supernova against those obtained from other techniques, such as the analysis of the cosmic microwave background or measurements of gravitational waves from merging neutron stars, helps to identify and mitigate systematic biases. The cosmic distance ladder, built rung by rung from nearby parallax measurements to distant supernova, represents one of astronomy's great collective achievements. Each method calibrates the next. Parallax, the apparent shift of a star's position as Earth orbits the Sun, provides direct geometric distances to stars within a few thousand light-years. These nearby stars include Cepheid variables, whose period luminosity relationship can be calibrated against the parallax distances. Once calibrated, Cepheids can measure distances to galaxies tens of millions of light-years away. Within some of those galaxies, type Ia supernova occur. And by measuring the distances to their host galaxies using Cepheids, astronomers calibrate the intrinsic luminosity of the supernova themselves. With that calibration established, type Ia supernova can then reach across billions of light-years, mapping the expansion history of the universe. This ladder is only as strong as its foundation. Errors at any level propagate upward, amplifying uncertainties at greater distances. For decades, one of the largest sources of uncertainty was the precise calibration of the Cepheid period luminosity relationship. Small errors in measuring the distances to nearby Cepheids translated into significant uncertainties in the distances to faraway galaxies. The Hubble Space Telescope made critical contributions here, observing Cepheids in galaxies far enough away to host type Ia supernova, allowing a more direct link between the two rungs of the ladder. More recently, the Gaia Mission, a space observatory, mapping the positions and distances of more than 1 billion stars in our galaxy, with unprecedented precision, has refined the parallax measurements that anchor the entire ladder, reducing systematic uncertainties and improving the overall accuracy of cosmic distance determinations. The standard candle approach also reveals the history encoded in light itself. When we observe a type Ia supernova in a galaxy with a redshift of 1, we are seeing an explosion that occurred roughly 8 billion years ago, when the universe was about half its current size. The light from that event has traveled through expanding space, its wavelength stretched, its energy diluted. By comparing supernova at different redshifts, astronomers reconstruct how the expansion rate has changed over time. In the distant past, when matter was denser, the expansion was slower. More recently, as dark energy has come to dominate, the expansion has accelerated. This history is written in the brightness and redshift of the supernova, a record preserved in the photons that have crossed the cosmos to reach our detectors. Yet the use of standard candles is not without controversy. Different methods for measuring the current expansion rate, known as the Hubble constant, have yielded results that do not perfectly agree. Measurements based on the cosmic distance ladder, using Cepheids and type Ia supernova, tend to produce a higher value than measurements derived from the cosmic microwave background. This discrepancy, sometimes called the Hubble tension, is small but statistically significant. It suggests either that there are unaccounted systematic errors in one or both methods, or that our model of the universe is incomplete. Resolving this tension is one of the most pressing challenges in cosmology, with implications for our understanding of dark energy, the early universe, and the fundamental physics governing cosmic expansion. Beyond supernova and Kyphids, astronomers have developed additional standard candles and related techniques. The tip of the red giant branchiphase of stellar evolution, where stars reach a maximum luminosity before transitioning to later stages, provides another distance indicator. Observations of the surface brightness fluctuations in galaxies, where the graininess of the light distribution depends on distance, offer yet another method. Gravitational lensing, where the gravity of a foreground galaxy bends and magnifies the light from a more distant object, can provide geometric distance estimates independent of standard candles. Each technique has strengths and weaknesses, and the convergence of results from multiple methods builds confidence in the overall picture. The shadows of dead stars thus become our guides through space and time. A supernova that exploded billions of years ago, its light now reaching us as a faint point against the backdrop of a distant galaxy, tells us not only how far away that galaxy is, but also how the universe has evolved since the explosion occurred. The consistency of these explosions, the fact that white dwarfs across the cosmos seem to obey the same physical laws, reaching the same critical mass and detonating with similar energy, speaks to the uniformity of nature on cosmic scales, the constants of physics, the behavior of matter under extreme conditions. The processes that govern stellar life and death all appear to be the same in distant galaxies as they are in our local neighborhood. This uniformity is not guaranteed. It is an empirical finding, tested and confirmed through observation. Or the laws of physics significantly different in distant regions or at earlier times, standard candles would not remain standard. Type Ia supernova might vary wildly in brightness, rendering them useless for distance measurement. The fact that they do not, that we can use them to map the expansion history over billions of years, suggests that the fundamental parameters governing nuclear fusion, quantum mechanics, and gravity have remained stable across most of the observable universe's history. This stability is itself a profound result, hinting at deep underlying principles that constrain the structure of physical law. The light curves of supernova also encode information beyond simple distance. The spectrum of a supernova reveals the composition of the ejected material, the velocity of the expanding debris, and the physical conditions during the explosion. By studying many supernova across a range of cosmic epochs, astronomers can investigate whether the properties of these explosions have evolved over time. So far, the evidence suggests remarkable constancy. Supernova that exploded when the universe was half its current age appear to follow the same physics as those exploding today. This consistency strengthens the foundation upon which the cosmic distance ladder rests, but it also raises questions. Why should the universe be so uniform? What mechanisms ensure that the same types of stars, the same critical masses, the same explosive processes recur across billions of years and billions of light years? These questions connect to broader issues in cosmology and fundamental physics. The uniformity of the universe on large scales, the constancy of physical laws, the predictability of stellar evolution are ingredients in the cosmological models we use to calculate the age of the universe. If any of these assumptions were significantly wrong, the calculated age would be correspondingly inaccurate. The agreement between different methods distances from supernova ages from the cosmic microwave background, constraints from the abundances of light elements forged in the first minutes after the Big Bang suggests that the assumptions are sound, at least to the precision currently achievable. But the small discrepancies that remain, such as the Hubble tension, serve as reminders that our understanding is still incomplete. Reading the shadows of dead stars is an act of reconstruction, piecing together a history from fragments of light scattered across space. Each supernova is a brief flare, a moment of violent transformation that sends ripples of information outward at the speed of light. By the time we detect that light, the explosion is ancient history, the debris long since dispersed into the interstellar medium. Yet, in the brightness and spectrum of that fading light, we find the clues needed to measure the vast distances between galaxies and to trace the expansion of the universe backward toward its origin. These measurements, painstakingly accumulated over decades, form the empirical backbone of cosmology, transforming abstract theory into concrete numbers, distances in billions of light-years, ages in billions of years, expansion rates measured to within a few percent. The universe, once an eternal and unchanging mystery, becomes a dynamic system with a measurable past, its history written in the light of dying stars. There was a time when eternity seemed self-evident. The universe, as conceived by the greatest minds of the early 20th century, was a stage that had always existed and would continue to exist without end. Stars might be born and die, planets might form and disintegrate. But the cosmos itself, the vast container within which all events unfolded, was eternal and unchanging. This was not mere philosophical preference. It was a conclusion drawn from the best available evidence and the most sophisticated theoretical frameworks of the era. Even Albert Einstein, whose general relativity had revolutionized our understanding of space, time, and gravity, initially believed that the universe must be static on the largest scales. Einstein's field equations, published in 1915, describe how matter and energy curve spacetime and how that curvature dictates the motion of objects. When he applied these equations to the universe as a whole, he encountered a problem. The equations did not naturally produce a static solution. A universe filled with matter should either expand or contract under its own gravity. There seemed to be no configuration that remained motionless, balanced indefinitely between collapse and dispersal. This troubled Einstein deeply, because a static universe was what observation appeared to demand. The stars showed no obvious signs of systematic motion toward or away from us. The cosmos seemed stable. To resolve this discrepancy, Einstein introduced a modification to his equations, a term he called the cosmological constant. This constant represented a kind of repulsive force inherent in the fabric of space itself, counteracting gravity and allowing for a static universe. It was an elegant mathematical fix, but it was also ad hoc, introduced not because the physics demanded it, but because the desired outcome required it. For a time, this seemed acceptable. The static universe, stabilized by the cosmological constant, became the standard model. Eternity was preserved, at least on paper. Meanwhile, at Mount Wilson Observatory in California, Edwin Hubble was conducting observations that would undermine this entire framework. Hubble was using the 100-inch Hooker telescope, then the most powerful instrument in the world, to study faint patches of light called nebulae. The nature of these nebulae was uncertain. Some astronomers believed they were clouds of gas within our own Milky Way galaxy. Others speculated that they might be distant island universes, separate galaxies lying far beyond the boundaries of our own. The debate was unresolved because no one had successfully measured the distances to these objects with any certainty. Hubble's breakthrough came through the identification of Cepheid variable stars within some of these nebulae. By measuring the periods of these pulsating stars and applying the period-luminosity relationship, he calculated their distances. The results were startling. The nebulae were not nearby clouds. Nope, they were galaxies, millions of light-years away, far beyond anything previously imagined. The universe was vastly larger than the Milky Way, populated by countless galaxies scattered through space. This discovery alone would have been revolutionary, expanding the known cosmos by orders of magnitude. But Hubble did not stop there. He began measuring the spectra of these distant galaxies, examining the wavelengths of light they emitted. What he found was a systematic pattern. Nearly every galaxy showed a redshift. Its light was shifted toward longer, redder wavelengths. Moreover, the degree of redshift correlated with distance. Galaxies that were farther away exhibited larger redshifts. The only plausible interpretation, given the known physics of light, was that these galaxies were moving away from us. the universe was not static. It was expanding. This observation, published in 1929, shattered the assumption of cosmic constancy. If galaxies were receding from one another, the universe could not be eternal and unchanging. It had to be evolving, growing larger with time. And if the universe was expanding now, logic dictated that it must have been smaller in the past. Run the expansion backward far enough, and everything would converge toward a single point, a moment of infinite density and temperature, a beginning. The universe, it seemed, had not always existed. There had been a time before which there was no time, a boundary beyond which the concept of before became meaningless. Einstein reportedly called the introduction of the cosmological constant his greatest blunder. The equations of general relativity had predicted an expanding universe from the start, but he had modified them to preserve the static model. Had he trusted the mathematics, he might have anticipated Hubble's discovery. Instead, the cosmological constant was discarded, and the expanding universe became the new paradigm. The concept of eternity, so deeply embedded in both scientific and philosophical thought, was replaced by the notion of a cosmos with a finite past universe that began at a specific moment and had been evolving ever since. Not everyone accepted this immediately. The idea of a cosmic beginning troubled many scientists, not on religious grounds, but on philosophical and scientific ones. If the universe had a beginning, what caused it? What existed before? These questions seem to push science beyond its proper domain, into realms of speculation and metaphysics. In response, some physicists developed alternative models that attempted to preserve the eternal nature of the cosmos, while still accounting for the observed expansion. The most prominent of these alternatives was the steady-state theory, championed by Fred Hoyle, Hermann Bondi, and Thomas Gold in the late 1940s. The steady-state model acknowledged that the universe was expanding and that galaxies were moving apart. However, it proposed that new matter was continuously being created in the voids between galaxies at just the right rate to maintain a constant average density. As galaxies receded and space expanded, new galaxies formed from the spontaneously appearing matter, filling in the gaps. In this picture, the universe had no beginning and no end. It had always looked roughly the same and would continue to look the same forever. The expansion was real, but it did not imply a starting point. The steady-state theory was intellectually appealing to those who found the notion of a cosmic beginning unsettling. It preserved a kind of cosmic democracy. No moment in time was privileged over any other. No location in space was special. The universe was homogeneous, not just in space, but also in time. However, the theory made specific predictions that could be tested. If the universe had always existed in roughly its current form, then the distribution of galaxies, the abundance of different types of astronomical objects, and the overall properties of space should be consistent with this eternal, steady state. Any evidence of evolution of the universe being significantly different in the distant past would contradict the model. Evidence for evolution came from multiple directions. Observations of distant galaxies revealed that they looked different from nearby ones. This was not merely a matter of distance, making them harder to see. Their properties, colors, spectra, the types of stars they contained suggested that galaxies had changed over time. The universe, when it was younger, appeared to have been a different place, populated by galaxies that were more active, more chaotic, undergoing more vigorous star formation. This was incompatible with the steady-state model, which required the universe to be the same at all epochs. The most decisive blow to the steady-state theory came not from the observation of galaxies, but from the detection of a faint glow permeating all of space. In 1964, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, were testing a sensitive radio antenna designed for satellite communications. They encountered persistent noise, a hiss of microwave radiation coming uniformly from every direction in the sky. No matter where they pointed the antenna, the signal remained. They checked for sources of interference. They cleaned bird droppings from the antenna. They accounted for every possible terrestrial or instrumental artifact. The noise persisted. What Penzias and Wilson had discovered, though they did not immediately realize it, was the cosmic microwave background, the relic radiation from the early universe. Theoretical work by George Gamow and his colleagues in the 1940s had predicted that if the universe began in a hot, dense state, it should have been filled with intense radiation. As the universe expanded and cooled, this radiation would have stretched to longer wavelengths, eventually becoming detectable as microwave radiation with a temperature of just a few degrees above absolute zero. The discovery of this radiation was direct evidence that the universe had once been far hotter and denser than it is today. It was the afterglow of the Big Bang, a fossil from the early moments of cosmic history. The existence of the cosmic microwave background was incompatible with the steady-state model. An eternal, unchanging universe had no mechanism to produce such a uniform bath of radiation. There was no event in the steady-state framework that would fill space with photons that had been cooling for billions of years. The microwave background could only be explained if the universe had evolved from a hot, dense beginning. This observation, combined with the evidence for galaxy evolution and the success of Big Bang nucleosynthesis in predicting the abundances of light elements, led to the abandonment of the steady-state theory by the vast majority of cosmologists. The universe was not eternal. It had a history. Fred Hoyle, one of the chief architects of the steady-state model, remained skeptical for many years, proposing modifications and alternative explanations. But the weight of evidence became overwhelming. The cosmic microwave background was not a fluke or a misinterpretation. Subsequent observations confirmed its thermal spectrum and its remarkable uniformity, properties that matched the predictions of the hot Big Bang model with extraordinary precision. The universe had once been a roiling plasma, opaque to light, and the microwave background was the echo of the moment it became transparent. No steady state could account for this. The shift from an eternal cosmos to a finite one was not merely a technical correction in cosmological models. It represented a fundamental change in how humanity understood existence itself. The universe was no longer a permanent backdrop, a given stage upon which the drama of matter and energy played out. It was an event, a process, something with a beginning, and, by implication, something that might have an end. Time was not an infinite continuum stretching in both directions, but a finite span that started with the Big Bang. Questions about what came before the beginning or what might happen after the end remained, but they were now framed in a context where the universe itself was a temporary phenomenon. This realization forced a confrontation with impermanence on the grandest possible scale. If the universe had a beginning, then everything within its star, every planet, every structure, every pattern was contingent, finite, destined to pass. The expansion that Hubble had observed was not merely a curious fact about galaxy motions. It was a feature of cosmic evolution, a process that connected the distant past to the distant future. The universe had been smaller, hotter, denser. It would become larger, cooler, more diffuse. The trajectory was not reversible. There was no return to a prior state, no cycling back to the beginning. Cosmic history had a direction. Einstein's reluctance to accept a dynamic universe had been understandable. A static cosmos aligned with centuries of philosophical thought that treated time as something external to the physical world, a dimension along which events occurred, but which itself did not change. An expanding universe, by contrast, made time intrinsic to the structure of the cosmos. The age of the universe was not an arbitrary parameter, but a consequence of its initial conditions and the laws governing its evolution. Time and space were woven together, both participants in the unfolding narrative of cosmic history. The cosmological constant, which Einstein had introduced and then discarded, would eventually return in a different form. Observations of distant supernova in the late 20th century revealed that the expansion of the universe was accelerating, driven by what is now called dark energy. Whether this dark energy is truly a cosmological constanta fixed property of empty space or Something more complex remains an open question. But the existence of this accelerating expansion adds another layer to the story. The universe is not only expanding, but doing so at an increasing rate, pulled apart by a mysterious force that constitutes the majority of its total energy content. This acceleration has profound implications for the ultimate fate of the cosmos. In an eternally expanding, accelerating universe, galaxies beyond our local group will eventually recede so far and so fast that their light will never reach us. The observable universe will shrink. Not because space itself is contracting, but because the expansion carries distant regions beyond the horizon of detectability. Stars will exhaust their fuel, galaxies will fade as star formation ceases, and eventually, even the most stable structures will dissolve. The universe will approach a state of maximum entropy, a cold, dark expanse where no gradients remain to drive change. This heat death is not an ending in the sense of an abrupt termination, but a gradual fading into quiescence, a universe that continues to exist, but in which nothing happens. The end of the eternal universe was thus also the recognition of an eventual ending. The steady state, if it had been true, would have implied perpetual renewal, an infinite future as well as an infinite past. The Big Bang model offered no such comfort. It gave the universe a birthday and, by extension, suggested that the universe would not persist unchanged forever. This was a sobering realization, though not an unexpected one once the expansion was understood. If the universe grew from a beginning, there was no reason to assume it would endure without transformation. The very processes that allowed stars to shine and galaxies to form were processes of energy dissipation, irreversible transformations that moved the cosmos toward equilibrium. Hubble's observations at Mount Wilson had thus opened a door that could not be closed. They revealed a universe in motion, a cosmos with a history and a future, both finite in their own ways. The age of the universe became a meaningful question, one that could be approached through observation and calculation. The 13.8 billion years derived from modern cosmology is the duration of this finite span, the interval between the moment of inception and the present. It is a number that carries with it the weight of cosmic impermanence, a reminder that even the grandest structures are temporary arrangements of matter and energy destined to dissolve as the universe continues its relentless expansion into an uncertain future. The universe leaves fingerprints in its creations. Every star that has ever burned, every galaxy that has ever formed, carries within its structure a record of the time that has passed since the beginning. These are not abstract timestamps, but physical signatures written in the distribution of elements, in the colors of starlight, in the architecture of stellar populations. To read these signatures is to access an independent clock, one that ticks not in seconds or years, but in the slow transformation of matter through nuclear processes spanning billions of years. Stars are engines of alchemy. In their cores, hydrogen fuses into helium, releasing energy that keeps the star luminous and prevents gravitational collapse. As a star ages and exhausts its hydrogen, it may progress to fusing helium into carbon and oxygen, and in the most massive stars, the chain continues: carbon into neon, neon into magnesium, oxygen into silicon, silicon into iron. Each stage produces heavier elements, forging the atomic building blocks of planets, life, and the rich chemistry of the universe. But these elements are locked within the star until its death. When a massive star exhausts its nuclear fuel, it collapses and explodes as a supernova, ejecting its enriched material into space. Successive generations of stars form from this increasingly contaminated gas, inheriting the products of their predecessors. The first stars that formed in the universe had no such inheritance. They emerged from clouds of primordial gas composed almost entirely of hydrogen and helium, the only elements produced in significant quantities during the first minutes after the Big Bang. These population 3 stars, as they are called, were massive and short-lived, burning through their fuel in mere millions of years before exploding. Their supernova scattered the first heavy elements into the surrounding medium, seeding it with carbon, oxygen, iron, and the rest of the periodic table. From this enriched gas, a second generation of stars formed population to stars containing small but detectable amounts of heavy elements. As this process repeated over billions of years, the metallicity of the universe gradually increased, with each generation of stars contributing to the growing reservoir of elements heavier than helium. This chemical evolution provides a chronometer. The metallicity of a star, the fraction of its mass composed of elements heavier than helium, indicates when it formed. Stars with very low metallicity are old. Formed early in the universe's history, when few generations of stars had lived and died. Stars with higher metallicity are younger, born from gas enriched by many cycles of stellar death and rebirth. By measuring the metallicities of stars in different environments, astronomers can infer the age of stellar populations and, by extension, the age of the structures they inhabit. Globular clusters are particularly valuable for this purpose. These are dense spherical collections of hundreds of thousands to millions of stars, all formed at roughly the same time from the same cloud of gas. Globular clusters orbit the halos of galaxies, ancient relics that have survived largely intact since their formation. The stars within them are metal-poor, indicating they formed early in cosmic history. By analyzing the ages of globular clusters through multiple independent methods, studying the luminosities and colors of their stars, modeling their evolutionary tracks, measuring the abundances of radioactive isotopes, astronomers can estimate when these clusters formed. The oldest known globular clusters in our Milky Way galaxy have ages around 13 billion years, placing them within a billion years of the Big Bang itself. This presents a crucial consistency check. If globular clusters are 13 billion years old, the universe cannot be younger than that. The age derived from cosmological observations, 13.8 billion years, comfortably accommodates the oldest stellar populations, leaving a window of time between the Big Bang and the formation of the first galaxies and star clusters. This agreement between independent methods strengthens confidence in both. The physics of stellar evolution and the dynamics of cosmic expansion converge on compatible timelines, each validating the other. The life cycle of stars also reveals something deeper about the current epoch. The universe is in what cosmologists call the stelliferous era, the age of stars. This is not a permanent condition. Star formation requires cold gas clouds that can collapse under gravity, and the supply of such gas is finite. As stars form, they consume hydrogen and lock it into stellar remnants: white dwarfs, neutron stars, black holes. Supernova and stellar winds heat the surrounding medium, making it harder for new clouds to collapse. Over time, the rate of star formation declines. The universe will not always be filled with shining stars. Calculations suggest that the era of vigorous star formation will last for roughly another 10 trillion years. Far longer than the current age of the universe, but still finite. We are thus living in the universe's youth. The majority of stars that will ever exist have not yet formed. The sky is bright with ongoing stellar births, with galaxies actively producing new generations of stars from their reservoirs of cold gas. This is a golden age, cosmically speaking, when the universe is rich in the raw materials for complexity, planets, chemistry, the potential for life. In the distant future, as the last stars exhaust their fuel and no new ones form, the universe will enter a darker, quieter era. The galaxies we see now, blazing with the light of billions of stars, will fade into collections of cold remnants. The chemical signatures in ancient stars allow us to peer back into the earliest epochs. Among the most metal-poor stars ever discovered are those with iron abundances 100,000th that of the Sun. These stars formed from gas that had been enriched by only one or two prior generations of supernova. They are witnesses to a time when the universe was still chemically pristine, when the first heavy elements were just beginning to pollinate the cosmos. Studying such stars offers a glimpse into conditions shortly after the first stars formed, roughly 100 million years after the Big Bang. Determining the ages of these ancient stars is challenging. Unlike globular clusters, where entire populations can be studied together, individual metal-poor stars must be analyzed one at a time. Age estimates rely on comparing observed properties, luminosity, temperature, surface gravity to theoretical models of stellar evolution. These models are sophisticated, incorporating detailed physics of nuclear reactions, energy, transport, and atmospheric processes. Yet they carry uncertainties, particularly for the oldest stars, where small differences in initial composition or assumptions about convection can translate into age uncertainties of 1 billion years or more. Radioactive dating offers an independent approach. Certain heavy elements, such as thorium and uranium, are produced only in specific astrophysical events, primarily supernova and neutron star mergers. These elements are radioactive, decaying over timescales of billions of years. By measuring the relative abundances of radioactive isotopes and their decay products in a star's atmosphere, astronomers can estimate how long ago those elements were created. This provides a lower limit on the star's age and, by extension, on the age of the galaxy. The technique is analogous to radiocarbon dating used in archaeology, but applied to cosmic timescales. The application of radioactive dating to stars is not straightforward. The abundances of elements like thorium and uranium in stellar atmospheres are extremely low, requiring the most sensitive spectroscopic observations. Moreover, the technique assumes that the radioactive elements were incorporated into the star when it formed and have not been significantly altered by processes within the star or contamination from external sources. Despite these challenges, measurements of thorium-to-rhenium ratios in some of the oldest known stars yield ages consistent, with the universe being around 13 billion years old, providing yet another independent confirmation of the cosmological timescale. The galactic chronometer is thus not a single clock, but a collection of interlocking timekeepers, each measuring cosmic age through different physical processes. Stellar evolution tracks the transformation of hydrogen into heavier elements and the gradual dimming of stars as they exhaust their fuel. Radioactive decay marks time through the irreversible transformation of unstable nuclei. The metallicity gradient in stellar populations records the cumulative history of element production across generations. These clocks do not always tick in perfect synchrony. Uncertainties in stellar models, observational limitations, and the complexities of astrophysical environments introduce scatter and disagreement. But they all point toward the same general conclusion: the universe is old, but not infinitely so. And the oldest objects we can observe formed relatively soon after the cosmic beginning. The architecture of galaxies themselves also bears witness to time. Spiral galaxies like the Milky Way are structured environments with ongoing star formation concentrated in their disks, while their spheroidal bulges and halos contain older, metal-poor stars. Elliptical galaxies, by contrast, are dominated by old stellar populations and exhibit little active star formation. These morphological differences reflect histories of formation and evolution. Spiral galaxies have retained reservoirs of cold gas, allowing star formation to continue. Elliptical galaxies underwent intense episodes of star formation early in their histories, consuming or heating most of their gas and leaving behind aging stellar populations. By studying the distributions of galaxy types at different redshifts, astronomers trace how the population of galaxies has evolved over cosmic time. Observations reveal that galaxies in the distant past, when the universe was younger, were more chaotic, more gas-rich, and more actively forming stars. Mergers between galaxies were more common, and the structures we see today had not yet fully assembled. The Hubble Space Telescope's deep-field images, capturing light from galaxies as they appeared billions of years ago, show a universe that was structurally different from the one we inhabit now. Galaxies were smaller, less organized, and often irregular in shape. This evolution from disorder to order, from vigorous activity to quiescence, is consistent with a universe that has aged, that has passed through distinct phases of development. The stellar populations in these distant galaxies can be analyzed through their integrated light, even when individual stars are not resolvable. By fitting models to the observed spectra, astronomers infer the ages, metallicities, and star formation histories of entire galaxies. The results indicate that some massive galaxies had already formed substantial stellar populations within the first few billion years after the Big Bang. This rapid assembly poses challenges for models of galaxy formation, requiring efficient mechanisms to funnel gas into galaxy centers and convert it into stars on relatively short timescales. The existence of these early, massive galaxies serves as a constraint on cosmological models and on the properties of dark matter, which provides the gravitational scaffolding for galaxy formation. The concept of the stelliferous era places our current epoch in a broader context. If we divide the history of the universe into eras based on the dominant sources of energy and structure, the stelliferous era is just one phase. It was preceded by the primordial era, lasting roughly the first 100 million years, when the universe was too hot and diffuse to form stars, filled instead with neutral hydrogen and the fading glow of the cosmic microwave background. The stelliferous era will eventually give way to the degenerate era, lasting from around 10 trillion to 100 trillion years from now, when star formation has ceased and the universe is populated by stellar remnants, white dwarfs, neutron stars, and black holes, along with planets and brown dwarfs. Beyond that lies the black hole era, when even these remnants decay through exotic processes. And finally, the dark era, when the universe consists of dilute radiation and particles drifting through an ever-expanding, ever-cooling void. We occupy a privileged position within this timeline. The stelliferous era, though long by human standards, represents only a small fraction of the universe's ultimate history. The conditions that allow for galaxies, stars, planets, and life are temporary. The raw materials for complexity-heavy elements forged in stars will persist for eons. But the energy sources that drive active processes will gradually fade. Stars will burn out. Black holes will evaporate. The universe will approach a state where change becomes imperceptibly slow, a frozen equilibrium from which no further evolution occurs. The galactic chronometer thus tells a story of maturation and decline. The universe began in a state of extreme energy and potential, rapidly expanding and cooling, transitioning through phases where different physical processes dominated. Stars ignited, galaxies assembled, heavy elements accumulated. We exist during the era when these processes are still vigorous, when the night sky is filled with light, when planets orbit stable stars and chemistry permits the emergence of life. This era is finite. It has a beginning, marked by the first stars, and it will have an end, marked by the last ember of stellar fusion fading into darkness. The connection between microscopic nuclear processes and macroscopic cosmic evolution is profound. The fusion of hydrogen in a stellar core is an event occurring at scales of atomic nuclei, governed by quantum mechanics and the strong nuclear force. Yet the cumulative effect of trillions upon trillions of such reactions over billions of years shapes the chemical composition of galaxies, determines the life cycle of stars, and sets the timeline for the universe's evolution. The age of the cosmos is written in these fusion reactions, in the gradual accumulation of helium and heavy elements, in the slow transformation of pristine primordial gas into the chemically rich environment we observe today. By studying the oldest stars, the most ancient globular clusters, and the evolutionary histories of galaxies, we access a physical record of cosmic time that complements and validates the measurements derived from the expansion of space and the cosmic microwave background. The universe is not only expanding at a measurable rate, but it is also aging in ways that leave tangible evidence: stellar populations with specific metallicities, galaxies with particular morphologies, clusters whose stars have reached predictable stages of evolution. These are the fingerprints of time, pressed into matter itself, enduring across the eons as testimony to the universe's finite but immense history. The galactic chronometer confirms what the redshifts and the microwave background indicate. We live in a universe that is approximately 13.8 billion years old in the midst of its stelliferous youth, a temporary brilliance against the backdrop of an eternity that stretches far into an uncertain and darkening future. There is a crack in the foundation. After decades of converging measurements, after the triumph of a cosmological model that seemed to explain the universe with remarkable precision, a discrepancy has emerged that refuses to resolve. Two independent methods for measuring the expansion rate of the universe yield results that do not agree. The difference is small, only a few percent, but it is statistically significant and persistent. No amount of refinement has made it disappear. This is not a minor technical issue. It suggests that something fundamental about our understanding of the cosmos is incomplete. The expansion rate, known as the Hubble constant, is one of the most important numbers in cosmology. It quantifies how fast the universe is growing, specifically how quickly galaxies at a given distance are receding from us due to the expansion of space. The Hubble constant is measured in units of kilometers per second per megaparsec, indicating how much faster a galaxy moves away for every additional megaparsec of distance. A higher Hubble constant means the universe is expanding more rapidly, which implies that less time has elapsed since the Big Bang for the universe to reach its current size. A lower value implies a slower expansion and a correspondingly older universe. For years, two primary approaches have been used to measure this constant. The first relies on observations of the early universe, particularly the cosmic microwave background. By analyzing the pattern of fluctuations in this ancient radiation and fitting them to cosmological models, researchers can infer the properties of the universe, including the expansion rate. This method looks backward, using the physics of the early cosmos to extrapolate forward to the present day. It is an indirect measurement, relying heavily on the accuracy of the cosmological model and the assumptions built into it. The second approach is more direct. It uses the cosmic distance ladder, starting with nearby stars whose distances can be measured geometrically, calibrating Cepheid variables in nearby galaxies, and then using those Cepheids to calibrate the luminosity of type Ia supernova. By observing supernova in distant galaxies and measuring both their brightness and their redshift, astronomers can determine the current expansion rate without relying on a detailed model of the early universe. This method looks outward and forward, building upward from local measurements to cosmic scales. These two methods should agree. They are measuring the same universe, the same expansion, yet they do not. The cosmic microwave background analysis, most recently performed by the Planck satellite, yields a Hubble constant of approximately 67 kilometers per second per megaparsec. The distance ladder method, refined using Hubble Space Telescope observations and other data, gives a value near 73. The gap is roughly 9% far larger than the uncertainties associated with either measurement. This discrepancy is what cosmologists call the Hubble tension. At first, the assumption was that one or both methods contained hidden systematic errors. Perhaps the distance ladder was miscalibrated. Perhaps the Cepheid period luminosity relationship was not as universal as assumed, varying slightly in different environments. Perhaps dust absorption was being underestimated, making supernova appear dimmer and thus more distant than they truly were. Alternatively, perhaps the cosmic microwave background analysis was flawed. Perhaps the cosmological model used to interpret the data was missing some component or process, or perhaps the assumptions about the early universe were incorrect. Researchers scrutinized every step, checking for biases, testing alternative models, cross-referencing with independent data. The tension persisted. Additional measurements using entirely different techniques have not resolved the issue. Observations of gravitational lensing, where the gravity of a foreground galaxy bends light from a more distant quasar, provide time delays that can be used to measure the Hubble constant independently of the distance ladder or the microwave background. Some of these measurements favor the higher value, others are intermediate. The picture remains muddy, with no clear consensus emerging from the full suite of observations. The persistence of the Hubble tension has led to a shift in perspective. What was initially treated as a measurement problem is increasingly viewed as a potential indication of new physics. If the discrepancy is real, if it is not the result of systematic errors, then it suggests that our standard cosmological model, despite its many successes, is missing something important. The model assumes a universe dominated by dark matter and dark energy, with ordinary matter making up only a small fraction of the total energy density. It assumes that the expansion history can be fully described by the Friedmann equations with these components. But what if there is an additional ingredient, some form of energy or field that affects the expansion in ways we have not accounted for? Dark energy itself remains one of the deepest mysteries in physics. Observations indicate that it makes up roughly 70% of the universe's total energy density, and that it has a repulsive gravitational effect, driving the accelerated expansion observed in distant supernova. The simplest model treats dark energy as a cosmological constant of fixed energy density inherent to the vacuum of space itself. This model fits the data remarkably well. But it offers no explanation for why the cosmological constant has the particular value it does. Theoretically, quantum field theory predicts a vacuum energy density many orders of magnitude larger than what is observed, a discrepancy so severe that it is known as the cosmological constant problem. If dark energy is not a simple cosmological constant, it might be a dynamic field that evolves over time. Such a field, sometimes called quintessence, could have different properties at different epochs in cosmic history. If the nature of dark energy has changed between the time the cosmic microwave background was emitted and the present day, it could alter the expansion rate in ways that are not captured by the standard model. This could reconcile the tension by making the early and late measurements consistent with each other, each correctly reflecting the expansion rate at their respective epochs, but within a modified framework that accounts for the evolution of dark energy. Another possibility involves early dark energy. It's a component that was significant in the very early universe but has since become negligible. If such a component existed, it would affect the physics of the cosmic microwave background and the expansion history in the first few 100,000 years after the Big Bang. This could shift the inferred Hubble constant from microwave background observations, without directly affecting the local distance ladder measurements. Models incorporating early dark energy have been proposed and can reduce the tension, but they introduce additional free parameters and must be tested against other observations to determine whether they are physically plausible. Modifications to the properties of neutrinos have also been considered. Neutrinos are nearly massless particles produced in vast numbers during the early universe. Their mass and interactions affect the expansion rate and the formation of structure. If neutrinos behave slightly differently than assumed in the standard model, perhaps interacting through previously unknown forces, the inferred Hubble constant from early universe observations could shift. This is a speculative idea, requiring new physics beyond the standard model of particle physics. But it illustrates the range of possibilities being explored. The Hubble tension also raises questions about the geometry and homogeneity of the universe. The standard cosmological model assumes that, on large scales, the universe is uniform in all directions, isotropic, and homogeneous. But what if we happen to reside in a region that is slightly denser or less dense than the cosmic average? If we are in an underdense region, a cosmic void, then galaxies outside this void would appear to be receding faster than the average expansion rate would suggest. This could artificially inflate the locally measured Hubble constant. However, for this explanation to work, the void would need to be enormous, hundreds of millions of light-years across, and we would need to be located near its center. Observations of the large-scale distribution of galaxies do not support the existence of such a large, special void centered on us. The universe appears statistically uniform on the relevant scales, making this explanation unlikely. Systematic errors remain a possibility that cannot be entirely dismissed. The cosmic distance ladder is a complex chain of measurements, each step calibrated against the previous one. Errors at any level can propagate upward, and subtle biases in how distances are measured or how data are selected can introduce shifts in the final result. The Gaia mission has improved parallax measurements for nearby stars, refining the foundation of the distance ladder. Further observations of Kyphids and supernova, conducted with different instruments and techniques, continue to test the robustness of the measurements. So far, the higher Hubble constant derived from the distance ladder has held up under scrutiny. But the possibility of an unidentified systematic error cannot be ruled out entirely. On the other side, the cosmic microwave background analysis depends on the cosmological model used to interpret the data. The Planck satellite measured the temperature fluctuations in the microwave background with exquisite precision. But extracting the Hubble constant from these measurements requires assumptions about the contents of the universe, the physics of the early plasma, and the processes that generated the fluctuations. If any of these assumptions are wrong, if there is some feature of early universe physics that the standard model does not capture, the inferred Hubble constant could be incorrect. The fact that multiple independent analyses of the microwave background data all yield similar results suggests that the measurement is robust within the framework of the standard model, but it does not guarantee that the framework itself is complete. The tension has philosophical implications as well. For the past few decades, cosmology has operated within a paradigm often called the lambda-CDM model, lambda representing the cosmological constant or dark energy, CDM standing for cold dark matter. This model has been extraordinarily successful, explaining a wide range of observations with a relatively small number of parameters. The discovery of the accelerating expansion, the precise measurements of the cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements all fit within this framework. The Hubble tension is the first significant crack in this edifice, a hint that the model may be incomplete, or that our measurements may be pushing into regimes where subtle effects become important. If the tension is resolved in favor of new physics, it would represent a major shift in our understanding. Dark energy, already mysterious, would become even more complex. The expansion history of the universe would need to be recalculated. The age of the universe itself might shift, though probably not by a dramatic amount. The difference between a Hubble constant of 67 and 73 translates to an age difference of only a few 100 million years, changing the estimate from roughly 13.8 billion years to perhaps 13.0 or 14.2 billion years, depending on the details. This is significant for precision cosmology, but it does not fundamentally alter the picture of a universe that is nearly 14 billion years old. Yet the implications extend beyond the age calculation. If the expansion rate has varied in unexpected ways, it affects our understanding of structure, formation, the growth of galaxies, the evolution of the universe over cosmic time. It touches on the ultimate fate of the cosmos. If dark energy is dynamic and evolving, the future expansion could unfold differently than current models predict. The universe might expand even faster than anticipated, or the acceleration might slow, or dark energy might even reverse its sign, leading to a future contraction. These scenarios remain speculative, but the Hubble tension opens the door to such possibilities. The scientific community is actively working to resolve the discrepancy. New telescopes and instruments, including the James Webb Space Telescope, are being used to observe Kyphids and supernova with greater precision, extending the distance ladder further and testing its calibration. Observations of the cosmic microwave background are being refined, with ground-based experiments and future space missions aimed at measuring polarization and other features that might reveal new physics. Gravitational wave observations from merging neutron stars, which produce both gravitational waves and electromagnetic signals, offer another independent method for measuring distances, and the Hubble constant one that does not rely on the traditional distance ladder or the microwave background. As these diverse approaches mature and more data accumulate, the tension may resolve in favor of one measurement, or it may deepen, forcing a revision of the standard cosmological model. What is clear is that we are at a frontier. The Hubble tension is not merely a technical puzzle, but a window into the limits of current theory. It reminds us that cosmology, despite its remarkable progress, remains an evolving science. The universe does not yield its secrets easily. Every measurement is hard-won, every theoretical framework provisional, the age of the universe, so often quoted as a definitive number, rests on a foundation of assumptions and observations that are continually being tested and refined. The 13.8 billion years is our best current estimate, supported by multiple lines of evidence, but it is not an immutable fact. It is a conclusion drawn from the data and models we have today, subject to revision as new information comes to light. The Hubble tension forces humility. It shows that even in areas where we thought we had achieved consensus, where the data seemed to converge and the models seemed robust, uncertainties can re-emerge. The universe may be more complex than we imagined, governed by forces and fields we have yet to identify. Or the tension may ultimately be resolved through better measurements and a deeper understanding of systematic errors, reaffirming the standard model and tightening the constraints on its parameters. Either outcome would be a victory for science, either the discovery of new physics or the confirmation that our methods, when carefully applied, can overcome subtle biases and yield reliable answers. For now, the tension stands as a question mark, a reminder that the age of the universe is not simply a number to be looked up, but a quantity inferred. Through intricate chains of reasoning and observation, it is tied to our understanding of expansion, of dark energy, of the structure of spacetime itself. The unseen forces that govern the cosmos, dark matter, dark energy. Whatever else may lurk beyond our current knowledge hold the key to resolving this mystery. Until we understand them fully, the precise age of the universe will remain, to some degree, uncertain. The 13.8 billion years is our best answer, a synthesis of what we know. But the Hubble tension suggests that the final word has not yet been spoken, that the universe still guards secrets about its own history, waiting for the next breakthrough to bring them into the light. The arrow of time points in one direction only. Eggs break but do not spontaneously reassemble. Heat flows from warm to cold, never the reverse. Stars burn their fuel and fade. They do not gather light back into themselves and grow younger. This irreversibility is captured by the concept of entropia, measure of disorder, of the dispersal of energy, of the number of ways a system can be arranged. The second law of thermodynamics states that the total entropy of an isolated system never decreases. It can remain constant in idealized reversible processes, but in reality, it always increases. The universe, taken as a whole, is the ultimate isolated system. It has no surroundings into which it can dump waste heat or from which it can draw fresh energy. Its total entropy has been rising since the beginning and will continue to rise until no further increase is possible. This inexorable climb toward maximum entropy defines the fate of the cosmos. Every process that occurs, every star that shines, every chemical reaction, every motion of matter generates entropy. Even the formation of complex structures like galaxies and planets, which might seem to represent local decreases in entropy, are accompanied by larger increases elsewhere as energy dissipates into the surrounding space. The net result is always an increase. Eventually, the universe will reach a state of thermodynamic equilibrium, where all available energy has been evenly distributed, all gradients have been erased, and no further work can be extracted from any system. This is the heat death, the silent end toward which the cosmos drifts. But the path to this end depends on the dynamics of expansion and the forces that govern it. 3 distinct scenarios have been proposed, each corresponding to different assumptions about the universe's composition and the nature of dark energy. These are not arbitrary speculations, but mathematical consequences of general relativity applied under varying conditions. Each leads to a different final state, though all share the common feature of being irreversible endpoints where the universe, in some sense, ceases to evolve. The first scenario is the Big Crunch. In a universe dominated by matter and devoid of dark energy, gravity acts as a brake on expansion. The mutual attraction of all matter pulls against the outward motion imparted by the Big Bang. If the density of matter exceeds a critical threshold, this gravitational pull will eventually halt the expansion. The universe will reach a maximum size and then begin to contract, all distances shrinking, galaxies accelerating toward one another, space collapsing back toward a singularity. As the contraction proceeds, the universe retraces its expansion in reverse. Galaxies merge. Stars collide, space becomes denser and hotter. The cosmic microwave background, which has been cooling for billions of years, would begin to heat up again, its photons blue-shifted by the contraction of space. Eventually, temperatures would rise to the point where matter disintegrates into plasma, then into a soup of fundamental particles, and finally into a singular point of infinite density, a mirror image of the Big Bang. This scenario was once considered plausible, even probable, when astronomers believed that the universe's expansion was decelerating due to gravity. But observations of distant supernova in the late 1990s revealed that the expansion is accelerating, not slowing. This acceleration implies that some form of repulsive energy, dark energy, dominates the dynamics of the universe. In the presence of accelerating expansion, a Big Crunch becomes impossible. The universe will not collapse. It will continue to expand, and the expansion will grow faster over time. The Big Crunch remains a theoretical possibility in models without dark energy or in hypothetical universes with different properties, but it does not describe the fate of our universe as we currently understand it. The second scenario is the Big Rip, a far more violent end. This occurs if dark energy is not a simple cosmological constant, but a dynamic field whose density increases over time. In the Standard Model, dark energy has a constant density as space expands. More dark energy appears, filling the new volume, but the density per unit volume remains fixed. However, if dark energy behaves as what is called phantom energy, its density could actually grow, exerting an ever stronger repulsive force. The expansion would accelerate without bound, eventually becoming so rapid that even structures held together by gravity or electromagnetic forces could not resist. In this scenario, the timeline to destruction is finite and surprisingly short on cosmic scales. Billions of years from now, galaxy clusters would be torn apart as the expansion overcomes the gravitational binding that holds them together. Galaxies would disperse. Later, individual galaxies would be ripped apart, their stars flung into the void as space expanded faster than gravity could pull them back. Later still, stars themselves would be torn apart, their plasma unable to hold together against the relentless stretching of space. Planets would disintegrate. Molecules would be pulled apart into atoms. Atoms would be ripped into nuclei and electrons. Eventually, even atomic nuclei would be shredded, protons and neutrons torn into quarks. Finally, space itself would be shredded, the fabric of spacetime torn asunder in a cataclysmic end. The Big Rip is a speculative scenario. There is no direct evidence that dark energy behaves as phantom energy. Current observations are consistent with a cosmological constant which does not lead to this fate. But the possibility cannot be entirely ruled out, and it serves as a reminder that the nature of dark energy remains unknown. If future measurements reveal that the density of dark energy is increasing, the Big Rip would become a real concern, shifting the ultimate fate of the universe from a slow fade to a sudden and violent termination. The third scenario, and the one most consistent with current observations, is the heat death. In a universe where dark energy behaves as a cosmological constant, the expansion continues forever, accelerating but not runaway. Galaxies beyond our local group recede beyond the cosmic horizon, their light redshifted into undetectability. Within gravitationally bound structures, our local group of galaxies, including the Milky Way and Andromeda expansion, does not tear things apart. Gravity holds these structures together, and they evolve in relative isolation as the rest of the universe fades from view. Star formation continues for trillions of years, but the supply of gas is finite. Over time, stars exhaust the available hydrogen. The smallest, longest-lived stars, red dwarfs, burn for tens of trillions of years, far longer than the current age of the universe. But eventually, even they run out of fuel. One by one, stars fade. The universe grows darker. The remaining light comes from cooling stellar remnants, white dwarfs, neutron stars. Brown dwarfs, objects that no longer produce energy but slowly radiate away the heat accumulated during their formation and active lives. White dwarfs cool over timescales of tens to hundreds of trillions of years, eventually becoming black dwarfs, gold. Inert lumps of crystallized carbon and oxygen, invisible against the darkness. Neutron stars cool more slowly, their immense gravitational binding energy taking even longer to dissipate. Planets continue to orbit these dead stars if they have not been ejected or consumed during the star's final stages. The universe becomes a graveyard. It's populated by dark remnants drifting through expanding space, no longer interacting, no longer evolving in any meaningful way. But even these remnants are not eternal. On timescales almost incomprehensibly long, processes that are negligible over billions or trillions of years become significant. Protons, the building blocks of atomic nuclei, may be unstable. Grand unified theories in particle physics predict that protons should decay. Though with half-lives of at least 10 to the 34 years, far longer than the current age of the universe. If protons do decay, then all matter composed of protons, every white dwarf, every neutron star, every planet, every particle of dust will eventually disintegrate. The atoms that make up these objects will dissolve into lighter particles and radiation. The process is slow beyond human comprehension, but given enough time, it is inevitable. Black holes complicate the picture. These are regions where gravity has compressed matter so densely that not even light can escape. Black holes form from the collapse of massive stars, from the mergers of stellar remnants, and from the accumulation of matter in galactic centers. They are the ultimate end state of gravitational collapse, and for a long time they were thought to be truly eternal, objects from which nothing could ever emerge. But in the 1970s, Stephen Hawking demonstrated that black holes are not entirely black. Quantum effects near the event horizon allow them to emit radiation, a process now known as Hawking radiation. This radiation is extraordinarily faint for astrophysical black holes. A black hole with the mass of the Sun would have a temperature of only a few millionths of a degree above absolute zero, emitting radiation so slowly that it would take 10 to the 67 years to evaporate completely. Supermassive black holes with millions or billions of solar masses would take even longer, 10 to the 100 years or more. These timescales are so vast that they dwarf the current age of the universe by factors beyond imagination. But they are finite. Given enough time, every black hole will evaporate, releasing its mass energy back into the universe as a diffuse spray of particles and radiation. After the last black hole evaporates, the universe will consist of a thin soup of photons, neutrinos, electrons, positrons, and perhaps other exotic particles, all spreading through an ever-expanding space. The temperature will approach absolute zero asymptotically, never quite reaching it, but coming arbitrarily close. The density of matter and energy will continue to drop as space expands. Eventually, the average separation between particles will be so great that they effectively never interact. The universe will have reached maximum entropy, a state where energy is perfectly evenly distributed, where no gradients exist to drive any process, where nothing happens because there is no potential for change. This is the heat death, also called the Big Freeze or the Big Chill. It is not an event, but a condition, a state of ultimate equilibrium. Time continues to pass, at least in a formal mathematical sense, but it loses physical meaning. There are no clocks, no processes that mark the passage of time, no observers to perceive it. The universe becomes a static, frozen expanse, incapable of supporting complexity, structure, or life. Entropy has reached its maximum, and the second law of thermodynamics, having driven the universe toward disorder for eons, finally achieves its inevitable conclusion. The concept of heat death was first articulated in the 19th century by physicists grappling with the implications of thermodynamics. If the universe is a closed system, and if entropy always increases, then the universe must eventually run down, its energy dissipated, its capacity for work exhausted. This was a troubling conclusion for thinkers accustomed to ideas of cosmic permanence or cyclical renewal. It suggested that the universe was not a perpetual motion machine, but a system with a finite lifespan of meaningful activity. The expansion of the universe, discovered later, reinforced this picture. An expanding universe that cools and dilutes over time naturally tends toward heat death. Yet the heat death is not total annihilation. Matter and energy still exist, just in forms that are maximally dispersed and disordered. The particles drifting through space have not vanished. They simply no longer interact in ways that produce complexity or organization. In some sense, the universe persists, but it is a universe devoid of stars, galaxies, planets, life, or any structure beyond the most elementary particles. It is a universe where the rich tapestry of phenomena that we observe today has unraveled into its simplest constituent threads, scattered across an infinite expanse. Philosophical questions arise when contemplating this end. Does time have meaning in a universe at maximum entropy? If nothing changes, if no processes unfold, then the passage of time becomes a purely abstract concept. Some physicists have argued that time itself might effectively cease in such a state, not in the sense that the temporal dimension disappears, but in the sense that there are no longer any clocks, no changes to measure, no way to distinguish one moment from another. The universe would be frozen not in space, but in state, locked in a configuration that persists unchanging for eternity. Other speculations venture even further. Quantum fluctuations, though extraordinarily rare in a universe at near-zero temperature and density, could still occur, over timescales incomparably longer than the age of the universe. Random fluctuations might, by pure chance, create localized regions of lower entropitemporary islands of order in an ocean of disorder. These fluctuations would be ephemeral, collapsing back into equilibrium almost immediately. But in principle, anything permitted by quantum mechanics, no matter how improbable, will eventually occur if one waits long enough. Could a new universe nucleate from such a fluctuation? Could a new Big Bang spontaneously arise? These are questions at the boundary of physics and speculation, touching on ideas that may not be testable, even in principle. The three paths to the end, Big Crunch, Big Rip, and heat death are not equally probable given our current understanding. The Big Crunch is ruled out by the observed acceleration of the expansion. The Big Rip remains a theoretical possibility, but lacks supporting evidence. The heat death, by contrast, is the natural outcome of a universe dominated by a cosmological constant, consistent with all current observations. It is the most likely fate, a slow fade into darkness and silence rather than a dramatic collapse or violent tearing apart. This fate is not imminent. The stelliferous era, the age of stars, will continue for trillions of years. Galaxies will evolve, stars will form and die, planets will orbit and perhaps harbor life. The universe as we know it has an immense future ahead of it, far longer than its past. But that future is bounded. The processes that give the universe its richness and complexity, nuclear fusion in stars, gravitational collapse into dense objects, The chemical reactions that underpin life are all entropy-generating processes, irreversibly converting useful energy into waste heat. Each one brings the universe one step closer to equilibrium, to the final state where no further work can be done. The measurement of the universe's age thus carries a shadow. To know when the cosmos began is to acknowledge that it will end. The 13.8 billion years that have passed since the Big Bang are part of a larger arc. A trajectory from low entropy to high, from concentrated energy to dispersed heat, from vibrant complexity to silent uniformity. The universe is mortal, not in the sense of ceasing to exist, but in the sense of ceasing to change, ceasing to sustain the dynamic processes that make it interesting. The stars will go out, one by one, and the night sky will grow darker, until eventually there is no light at all, no warmth, no motion, no lie. The cold, empty expanse of space, expanding forever into an eternity of nothingness. This is the silent end, the heat death, the final equilibrium toward which all paths ultimately lead. There will come a time when the sky goes dark. Not suddenly, not through catastrophe, but through the patient, relentless expansion of space. Galaxies that now populate the night sky, visible as faint smudges through our telescopes, will fade from view. Their light already stretched into the red by billions of years of travel through expanding space, will be redshifted beyond detection. The photons will still be traveling toward us, but their wavelengths will have been pulled so long, their energy so diluted that no instrument, no matter how sensitive, will be able to detect them. One by one, the galaxies will vanish, not because they have ceased to exist, but because the space between us and them has grown too vast for light to bridge. This is the consequence of accelerating expansion. Dark energy, that mysterious component making up the majority of the universe's energy density, exerts a repulsive gravitational effect that drives space to expand faster over time. As the expansion accelerates, distant galaxies recede at ever-increasing speeds. There is a boundary, called the cosmic event horizon, beyond which galaxies are receding faster than light can travel through the expanding space. Galaxies beyond this horizon are causally disconnected from us. No signal, no information, no light they emit will ever reach us, no matter how long we wait. And as time passes, this horizon shrinks. In moving coordinates, more and more galaxies slip beyond it, carried away by the accelerating expansion. Within our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions' gravity hold sway. These galaxies are gravitationally bound, their mutual attraction strong enough to resist the expansion of space. Over the next few billion years, the Milky Way and Andromeda will collide and merge, forming a single, larger elliptical galaxy. The other members of the local group will also merge or be absorbed. Eventually, our local cluster will settle into a relatively stable configuration. A single massive galaxy or a small system of galaxies orbiting one another. But beyond this local structure, the universe will fade. Already, the most distant galaxies we can observe are seen as they were when the universe was young. Their light has taken billions of years to reach us, and during that journey, space has expanded, carrying those galaxies far beyond the distances implied by the light travel time. Some of the galaxies we observe now are already beyond the cosmic event horizon. We see them because the light we detect was emitted billions of years ago, before they crossed that boundary. But no light they emit today will ever reach us. We are seeing their past, and we will never see their future. As the expansion continues, fewer and fewer galaxies remain within our observable universe. 100 billion years from now, the descendants of today's civilizations, if any survive, will look out into a sky almost devoid of external galaxies. The cosmic microwave background, that faint echo of the Big Bang, will have cooled and redshifted to the point of near-end detectability. The evidence that the universe is expanding, that it had a hot, dense beginning, that it contains billions of other galaxies, all of this will have faded beyond the reach of observation. future astronomers will be left with only the local galaxy isolated in an otherwise empty cosmos. This is the information horizon, the boundary beyond which knowledge cannot penetrate. It is not a physical barrier, but a consequence of the geometry of spacetime and the finite speed of light. In a universe with accelerating expansion, the observable universe does not grow indefinitely. It reaches a maximum extent and then begins to shrink, not because space itself is contracting, but because the expansion carries distant regions beyond the reach of observation faster than light from those regions can arrive. The implications are profound. Cosmology, as we practice it today, depends on observing distant galaxies. Mapping the large-scale structure of the universe, analyzing the cosmic microwave background. These observations allow us to infer the history of the cosmos, the processes that shaped it, the parameters that govern its evolution. But all of this evidence will eventually disappear. Future civilizations arising in a universe billions of years older than our own will have no way to discover that the universe is expanding, no way to infer the Big Bang, no way to know that their galaxy is not the entirety of the cosmos. They will inherit a universe that appears static and eternal. Much like the universe our ancestors believed in before, Hubble's observations revealed the truth. The information horizon thus marks the end of an era, during which the universe can be understood through observation. We live in a privileged epoch when the universe is old enough to have formed stars and galaxies and complex structures, but young enough that the evidence of its dynamic history is still visible. This window is temporary. It is a brief interlude in the vastly longer timeline of cosmic evolution, a moment when the universe reveals its secrets to those capable of observing them. The timeline of this fading is measured in trillions of years, far beyond the lifespan of any star currently burning, far beyond any conceivable human timescale. Yet it is finite. The expansion does not pause. The acceleration does not reverse. The universe will not return to a state where distant galaxies are once again observable. The loss is irreversible. Information, once lost beyond the horizon, is gone forever, at least from the perspective of any observer within the observable universe. This loss extends to more than just galaxies. As the universe ages and enters the degenerate era, when stars have ceased to shine and stellar remnants dominate, even the local environment will become information poor. Black holes, those ultimate information sinks, will have evaporated through Hawking radiation. The particles that once comprised stars, planets, and the remnants of civilizations will have decayed or dispersed. The universe will be filled with a dilute gas of photons and light particles, no longer organized into structures that carry meaningful information about the past. Entropy in this context can be understood as the loss of information. A low entropy state is one where information is concentrated, where patterns exist, where the arrangement of matter and energy is far from random. A high entropy state is one where information has been erased, where everything has been mixed and dispersed to the point that no patterns remain. The universe began in a low-entropy state, highly ordered, with matter and energy concentrated into a hot, dense plasma. Over time, entropy has increased, structures have formed and dissolved, energy has been dissipated, and information has been spread across ever larger volumes. The final state, the heat death, is one of maximum entropy, where all information has been lost, where the history of the universe is no longer recoverable from the state of the system. The concept of the information horizon thus ties together the physical expansion of space, the thermodynamic arrow of time, and the epistemological limits of what can be known. The universe is not only aging and cooling, it is also forgetting. The details of its past are gradually being erased, the evidence scattered and redshifted into obscurity. We are fortunate to exist at a time when the memory of the Big Bang is still accessible, when the cosmic microwave background can still be detected, when distant galaxies can still be observed. But this fortune is temporary. The philosophical weight of this realization is considerable. Humanity, and any other intelligent life that might exist, finds itself in a universe that is not only vast, but also ephemeral in its capacity to be understood. The window during which the cosmos is both complex enough to support observers and transparent enough to be observed is narrow. Before this window, the universe was too hot, too dense, too chaotic for stars and planets to form. After this window, the universe will be too cold, too empty, too dark for meaningful observation, or perhaps even for life itself. This places our existence in a particular temporal context. We are not at the beginning of the universe's story, nor are we near its end. We are somewhere in the middle of the stelliferous era, during a period when stars are abundant, galaxies are bright, and the evidence of cosmic history is still legible. This is not an accident. Complex structures like stars and planets require specific conditions, temperatures that allow nuclear fusion, but not so high that matter cannot condense. Densities that permit gravitational collapse, but not so extreme that everything collapses into black holes. Life, if it requires planets and stars and the chemistry enabled by heavy elements, can only arise during this particular epoch. The anthropic principle offers one way to think about this. Observers can only exist during epochs, when conditions permit the existence of observers. We should not be surprised to find ourselves in a universe that is roughly 10 billion years old, because this is the timescale required. 4 stars to form, 4 heavy elements to be synthesized and distributed, 4 planets to coalesce, and for life to evolve. Universes much younger would lack the chemical complexity. Universes much older might lack the energy sources and observational access needed to develop advanced understanding. We exist when and where we do, because these are the conditions compatible with our existence. Yet this explanation, while logically sound, does not diminish the poignancy of the realization that the universe's richness is temporary. The stars that currently fill the sky are not permanent fixtures. They are transient phenomena, localized concentrations of energy that will fade over time. The galaxies that we map and study are snapshots of structures in the process of evolving and, eventually, dissolving. The cosmic microwave background, that ancient light from the early universe, is growing fainter with each passing moment as space expands and its photons lose energy. Everything we observe is part of a fleeting configuration, a brief arrangement of matter and energy that will not endure. The concept of deep time, which earlier chapters explored as a cognitive challenge, takes on a new dimension here. It is not only that the timescales of the universe exceed human intuition, but that the universe itself is divided into eras with fundamentally different characters. The primordial era, the stelliferous era, the degenerate era, the black hole era. The dark era. These are not merely labels, but descriptions of qualitatively distinct phases of cosmic evolution. Each era has its own processes, its own structures, its own possibilities. We inhabit one such era, and our understanding of the universe is shaped by the characteristics of this particular moment in its vast timeline. The loss of observational access in the far future raises questions about the nature of knowledge and reality. If future civilizations arise in a universe where all evidence of the Big Bang has disappeared, where the expansion is no longer observable, where the cosmic microwave background has faded into undetectability, will they be able to discover the true nature of their cosmos? Or will they construct alternative cosmologies, perhaps static models like those of Einstein's era, unaware that they are living in the aftermath of a dynamic, evolving universe? The information required to infer the Big Bang will no longer exist in their observable environment. The history of the universe will be, in a real sense, unknowable to them. This suggests a disturbing possibility. Could we, in our own time, be in a similar position? Might there be aspects of cosmic history that occurred so long ago, or on scales so large, that the evidence has already faded beyond detection? The universe we observe might be a palimpsest, layers of history written over one another, with the earliest layers erased by the passage of time and the expansion of space. Our cosmological models are based on the data available to us, But we cannot know what data has been lost. We cannot rule out the possibility that there are earlier epochs, prior cycles, or processes that have left no observable trace. Some theoretical frameworks attempt to address this. The idea of eternal inflation, for instance, suggests that the Big Bang we observe was not the absolute beginning, but a local event within a larger, eternally inflating multiverse. In this picture, universes like ours are constantly being created within the inflating background, each with its own initial conditions and observable properties. Our observable universe would be just one bubble among countless others, most of which are forever beyond our reach, separated by vast expanses of inflating space. The information horizon in this context is not only a future boundary, but also a boundary in space and perhaps in time, cutting us off from knowledge of the larger structure within which we are embedded. These ideas push at the limits of what can be tested empirically. If a hypothesis predicts phenomena that lie beyond the information horizon, it becomes difficult or impossible to verify through observation. This does not make such hypotheses unscientific. They can still be motivated by theoretical considerations, by the internal consistency of physical laws, by their ability to explain observed phenomena more elegantly than alternatives. But it does mean that certain questions about the universe may never be answerable with certainty. The information horizon imposes a fundamental limit on empirical knowledge. Yet within the boundaries of what is observable, remarkable progress has been made. The age of the universe, the expansion rate, the composition of matter and energy, the history of structure formation, all of these have been measured and mapped with increasing precision. The 13.8 billion years since the Big Bang represent a vast span of time during which the universe has transformed from a nearly uniform plasma into a structured cosmos filled with galaxies, stars, planets, and life. We have learned to read the history written in light, in the spectra of distant galaxies, in the fluctuations of the cosmic microwave background, in the chemical compositions of ancient stars. This knowledge is itself a kind of triumph over the constraints of time and space. We are creatures of the moment, with lifespans measured in decades, inhabiting a planet orbiting an ordinary star in an unremarkable galaxy. Yet through observation, reason, and the accumulation of evidence, we have reconstructed the history of the entire cosmos, traced its evolution across billions of years, and understood the physical laws that govern its behavior. We have measured the age of the universe with precision, determined the fate that awaits it, and confronted the unsettling reality that the window of observability is closing. The final horizon of information is both an ending and a beginning. It is an ending because it marks the point beyond which observational cosmology becomes impossible, where the evidence of cosmic history fades into darkness. But it is also a beginning in the sense that it challenges us to extract every possible insight from the data we have now to understand as deeply as we can while the universe is still willing to reveal its secrets. The stars will fade, the galaxies will vanish, the microwave background will cool into nothingness. But for now, the sky is full of light, and the story of the universe is still legible in that light. We stand at a unique vantage point, temporally positioned to witness the cosmos in its full glory, to measure its age, to trace its history, and to contemplate its ultimate fate. The information is here, now, waiting to be gathered and understood before the expanding darkness claims it forever. We are late arrivals to an ancient story. The universe had been unfolding for more than 9 billion years before the sun ignited, before the Earth coalesced from the protoplanetary disk, before the first simple cells emerged in primordial oceans. For the vast majority of cosmic history, there was no witness. Stars burned, galaxies collided, supernova scattered heavy elements across space, and none of it was observed or understood. The universe evolved in silence, without awareness of itself, governed by physical laws that operated indifferently to the structures they created. Then, on at least one small planet orbiting an unremarkable star, something unprecedented occurred. Matter organized itself into forms capable of self-replication, of metabolism, of responding to the environment. Over billions of years, through processes of variation and selection, life grew more complex. Nervous systems emerged, brains developed, consciousness arose. Eventually, one lineage of organisms became capable of abstract thought, of language, of cumulative cultural knowledge. Humans appeared, and with them, the capacity to ask questions about the cosmos itself. This capacity is extraordinary. It is not merely that we exist, but that we can reflect on our existence, that we can measure the age of the universe, trace its history, predict its future. The atoms in our bodies were forged in the cores of stars that died billions of years ago. We are, quite literally, made of stardust. The recycled remnants of stellar nucleosynthesis scattered across space by supernova and gathered into new generations of stars and planets. The universe has, through us, become aware of itself. It has developed the means to observe its own structure, to understand the laws that govern its evolution, to contemplate its origins and its fate. This self-awareness is fragile and contingent, depends on conditions that are neither universal nor permanent. Life, as we understand it, requires liquid water, stable energy sources, a rich chemistry of heavy elements, and a relatively benign environment shielded from excessive radiation and gravitational extremes. These conditions are not common in the universe. Most of space is empty, most environments are hostile, and most matter is locked into stars, black holes, or diffuse clouds where chemistry cannot occur. Earth, and presumably any other world that harbors life, occupies a narrow niche of habitability within a vast expanse of inhospitable space. Moreover, the window during which such conditions exist is limited. In the early universe, before the first stars formed and enriched space with heavy elements, there were no planets as we know them. The first generations of stars were massive and short-lived, burning through their fuel in millions of years and exploding before complex structures could develop around them. Only after several cycles of stellar birth and death did the interstellar medium become sufficiently enriched with carbon, oxygen, nitrogen, and other elements necessary for planets and life. This process took billions of years. We exist because we are late, because enough time has passed for the universe to prepare the stage, but we are also early. The Stelliferous era will continue for trillions of years, far longer than the current age of the universe. Most stars that will ever exist have not yet formed. If life is possible around those future stars, and if civilizations arise to contemplate the cosmos as we do, they will inherit a universe much older than ours, one where the evidence of the Big Bang has faded, where fewer galaxies are visible, where the cosmic microwave background has cooled into near-end detectability. They will face greater challenges in reconstructing cosmic history. We, by contrast, exist at a time when the universe is still legible, when the traces of its origin are still accessible to observation. This places us in what might be called the golden age of cosmology. The universe is old enough to have produced complexity galaxies, stars, heavy elements, planets, life but young enough that the history of its formation is still observable. The cosmic microwave background still glows faintly in the sky. Distant galaxies, though receding, are still within reach of our telescopes. The expansion is measurable, the age calculable. Future civilizations arising billions of years from now will not have these advantages. Past civilizations, had they existed in the early universe, would not have had the stable stars or heavy elements needed for their development. We occupy a temporal sweet spot, a brief interval when the universe can be both inhabited and understood. Yet this understanding reveals a sobering truth. The universe is not tailored to our needs or our presence. It is not a home in any permanent sense. It is a temporary arrangement of matter and energy, evolving according to physical laws that care nothing for consciousness, for meaning, for survival. The stars that provide the energy for life will burn out. The galaxies that populate the sky will fade beyond observation. The structures that make the universe interesting: planets, stars. Galaxies will dissolve over timescales so vast that human existence, even the existence of our entire species, is an infinitesimal flicker in comparison. This realization might seem bleak. If the universe is heading toward heat death, if all complexity is destined to dissipate, if consciousness itself is a transient anomaly in a cosmos trending toward silence and darkness, what significance can our existence have? The question has troubled philosophers and scientists since the implications of thermodynamics and cosmic expansion became clear. If everything ends, if entropy always increases, if the universe ultimately forgets every structure it ever produced, then what is the point? One response is to recognize that significance does not require permanence. A symphony does not lose its beauty because it ends. A sunset is not less striking because night will follow. The universe, in its current state, is filled with structure and complexity: galaxies swirling through space, stars igniting and dying, planets orbiting in intricate dances, life emerging and evolving. These are phenomena of immense richness, regardless of whether they persist forever. The fact that they are temporary does not diminish their reality or their capacity to be appreciated. Moreover, consciousness itself is a rare and remarkable feature of the universe. For nearly 14 billion years, the cosmos evolved without awareness. Now, at least here, it has produced beings capable of understanding it. This is not a minor achievement. It is the universe attaining knowledge of itself, a kind of cosmic self-reflection. We are the means by which the universe observes, measures, comprehends. In us, the laws of physics have led to minds capable of discovering those very laws. This recursive loop matter, organized in such a way that it can understand the principles governing matter's one of the most profound outcomes of cosmic evolution. The brevity of our existence, measured against cosmic timescales, does not negate this significance. A brief witness is still a witness. The fact that human consciousness will eventually cease, that our species will likely be extinct long before the stars burn out, does not erase the observations we have made, the understanding we have achieved, or the questions we have asked. The universe, for a brief moment in its vast history, has been understood. It has been measured, mapped, contemplated. That moment is now. There is also the possibility that we are not alone. The universe is immense, containing hundreds of billions of galaxies, each with hundreds of billions of stars, many of which likely host planets. The conditions that led to life on Earth's liquid water, stable energy sources, organic chemistry, are not unique to our world. They exist or have existed elsewhere. If life has arisen more than once, other civilizations have developed the capacity to observe and understand the cosmos, then the universe has been witnessed in multiple places, at multiple times. We may be part of a broader pattern, one instance among many of the universe becoming aware of itself. Yet, even if we are alone, even if consciousness is an extraordinary fluke that occurred only once in the entire observable universe, that does not diminish its value. Rarity does not imply insignificance. A single diamond in a vast desert is not worthless because it is surrounded by sand. Consciousness, with its capacity for understanding and meaning-making, is precious precisely because it is rare, because it represents a departure from the default state of inert matter governed by entropy and expansion. The golden age of astronomy in which we find ourselves is thus both a privilege and a responsibility. We have access to information about the universe that future civilizations may not. The cosmic microwave background, the redshifts of distant galaxies, the nucleosynthesis of light elements in the first minutes after the Big Bang. All of this evidence is available to us now, but it will fade. If we do not observe it, measure it, and preserve the knowledge we gain, it may be lost forever. We are custodians of cosmic history, charged with understanding the universe while the evidence still exists. This understanding is cumulative. Each generation builds on the discoveries of the previous one, refining measurements, testing theories, pushing the boundaries of what is known. The 13.8 billion years we now accept as the age of the universe is the result of centuries of observation and thought from the first telescopes revealing the moons of Jupiter to the space-based instruments mapping the cosmic microwave background. The knowledge we have assembled is a collective achievement, a testament to human curiosity, ingenuity, and persistence. It is also inherently fragile. Knowledge is not self-sustaining. It must be transmitted, taught, preserved. Civilizations can rise and fall. Libraries can burn. Languages can be forgotten. The scientific understanding we have achieved is a cultural artifact, dependent on institutions, technologies, and traditions that must be actively maintained. If humanity were to disappear tomorrow, the universe would continue as before, but the knowledge we have gathered would vanish with us. The stars would still shine, the galaxies would still recede, but there would be no one to observe or understand them. This fragility underscores the importance of the present moment. We exist at a time when the universe is both comprehensible and observable, when the tools and methods to study it are available, when the evidence of its history is still accessible. This confluence is temporary. In the distant future, the universe will be darker, emptier, less conducive to observation. In the distant past, it was too chaotic, too simple, incapable of supporting the structures necessary for life and consciousness. Now, in this narrow window, we have the opportunity to understand, and we have made remarkable progress. We have measured the age of the universe to within a few tens of millions of years, a precision of better than 1%. We have traced its history from the first fraction of a second after the Big Bang to the present day. We have identified the major components of ordinary matter, dark energy, and quantified their contributions. We have observed the evolution of galaxies, the life cycles of stars, the synthesis of elements. We have built models that predict the future, extending our understanding trillions of years forward to the eventual heat death. This knowledge does not answer every question. The Hubble tension remains unresolved. The nature of dark matter and dark energy is unknown. The ultimate fate of the universe, while predictable in broad strokes, depends on details we have not yet pinned down. There are mysteries we have not even begun to address: why the universe exists at all, why the laws of physics take the form they do, whether there are other universes beyond our own. But the progress we have made is undeniable. From a position of near total ignorance about the cosmos, we have constructed a detailed, quantitative, testable picture of its structure and history. The journey to this understanding has been driven by a fundamental human impulse, the desire to know. This impulse transcends practical concerns. Understanding the age of the universe does not help us grow crops, build shelters, or cure diseases. It does not extend individual lifespans or increase material comfort. Yet we pursue it anyway, because knowing is intrinsically valuable, because the universe is vast and mysterious, and we are compelled to make sense of it. This drive to understand is as much a part of human nature as any other trait. And it has led us to insights that would have been inconceivable to our ancestors. We are, in this sense, the brief witness in the dark. We emerged from the darkness of ignorance and will eventually return to it as individuals and perhaps as a species. But for now, we see. We observe the cosmic microwave background, the remnant light from an era before galaxies existed. We measure the redshifts of distant supernova, tracing the expansion history of space itself. We calculate the ages of the oldest stars, finding them consistent with a universe nearly 14 billion years old. We stand on a small planet, gazing outward into immensity, and we comprehend, at least in part, what we are looking at. This comprehension is a kind of defiance. The universe may be indifferent to our existence, trending inexorably toward entropy and equilibrium, but we are not indifferent to it. We measure, we analyze, we seek to understand. We construct meaning in a cosmos that offers none inherently. We find beauty in the patterns of galaxies, in the elegance of physical laws, in the realization that we are connected to the stars through the atoms in our bodies. The universe does not care, but we do, and that caring transforms our experience of existence from passive endurance to active engagement. The age of the universe, 13.8 billion years, is not just a number. It is a marker of everything that has happened, every star that has burned, every galaxy that has formed, every process that has led to this moment when matter organized itself into beings capable of asking how old the universe is. It is a reminder that we are part of a vast, ancient, evolving cosmos, that our existence is both insignificant in scale and profound in its capacity for awareness. We are the universe looking at itself, a brief flicker of consciousness in the long night, measuring the darkness and finding it filled with light.